search in action. So we are talking about search stuff for multimodal data. My name is Yusuke from the University of Tokyo. Okay, let's first introduce ourselves. Again, my name is Yusuke from Tokyo. I'm doing image retrieval stuff or large-scale indexing stuff. And like this one, I presented some work in the ICAS. This one is an ARM implementation of neural network search in Face, the famous Facebook library. So our team is the also ARM implementation. And I did some previously. I did some tutorial for neural network search in the previous CVPR, like this one. Okay. Then Martin, you think?
Yes. So hi everyone, thanks for coming. My name is Martin. I'm an associate professor at the IT University of Copenhagen. And what I do is usually theory of similarity search and nearest neighbor search. So I design nearest neighbor search system that use hashing, and then you get some provable guarantees. What I also do, because this doesn't work that well empirically, what I also do is I do benchmarking and workload generation. And what I do there is I run benchmarks on million scale nearest neighbor search. I also run benchmarks on billion scale nearest neighbor search, and that's what I'm going to tell you about today. Cool.
Okay, and the third speaker is Han. Unfortunately, he can't come here. So, are you in Zoom, Han? No, no yet. Okay, okay. So Han is the founder of Gina AI, which is an AI startup company in Germany, and he is doing some very interesting open source application like Gina AI stuff. So he will introduce that in his talk. Okay. Okay, so today, again, we are doing some multimodal search stuff. So this is one example. It's very popular one. I mean, it's very easy one. Given the query of text, in this case, to dog spraying in the snow, then we have database here, image database. And let's find the similar one. So in this case, the answer is this one, right? So this is multimodal search. So today in our talk, so how to make this stuff fast and how to implement this one. So we will discuss something like that. Another example is here, a large language model. As everyone knows, so GPT-3 is GPT-3, GPT-4 are very popular, right? So in this, one of the most easy way to put information, put our knowledge to LLM is embedding. You know, given this text query plus like Wikipedia data, we can do some more sophisticated stuff, composition using GPT. And this part is actually search, you know. So we will discuss this kind of things. Okay, so our target audience is those who want to try neural search, or those who have tried neural search but would like to know more about theory, algorithm inside. And our talk is three parts. The first part, I will explain something like medium scale search. So medium scale means so every data can be loaded on the memory. So memory search on the memory. You know. The next part, so Martin will explain billion scale search. So in that case, so often all data cannot be loaded on the memory. So it's kind of hard task. You know. And finally, Han will introduce some very interesting his open source project, doc array, which is a very foundation of data representation for multimodal stuff. So it's interesting. Okay. This is a schedule. Now I finish my opening talk. Then I start my talk 50 minutes. Then Martin 50 minutes. Then break. Then Han 50 minutes. Okay. So let's start. Okay. Okay. Thanks for coming again. So it's a lot of people here. It's kind of surprised me. Okay, so theory and application of graph-based search. That's my talk. Okay, this is introduction slide, so I already finished. Okay, so this is a table of contents today. So first, I introduce a background of these whole things. Then I introduce a graph-based search, especially some basic stuff. So how to construct graph and how to do search. Then after that, I show some observation, some very fundamental things. After that, I show some properties of graph-based stuff. Then I show some representative work. One of the most famous one is HNSW. Maybe some of you have already used that. After that, I show NSG and GT and Vamana. And I conclude my talk with discussion. Okay, so first I show some background. Okay, my talk is about, again, nearest neighbors. Can I, maybe. Yeah. Okay, my talk is about nearest neighbor search. Let's say we have n d-dimensional vectors, xn, n equal 1 to n. So there's a lot of database vector here. Okay. There are a lot of database vector here. Then our task is search. So given a query vector, this guy, query vector Q, our task is to run this mathematical equation, Q minus xn. So this is L2 square distance. So let's find the most closest one to the database vector. In this case, we can get this one, right? And this one is actually very similar to this one. That's fine. So this nearest neighbor search is a kind of fundamental operation in computer science, right? So everyone needs to solve this one. And obviously, it's very easy to solve. We can do some linear scan. Then this cost is O of ND. This is slow, actually. Slow means because this is the function of n. So if the data is double, then runtime is also double, right? One thing is, today I talk about L2 square distance here, but sometimes this is inner product or something. So it's a kind of very many variant, but it's fine. Okay. Okay. Anyway, so this is slow. So what should we do? So we do approximate nearest neighbor search. So let's say approximate version. So it's fast because it's approximate, and this don't necessarily have to be exact neighbors. So sometimes it fails, but that's fine. So there's a trade-off: the runtime, accuracy, and memory consumption. Obviously, if we want to achieve fast search, then accuracy is not enough in some cases. So that's the thing. Okay. Okay, and in this talk, I suppose n is like less than 1 billion. As I say, it's like million scale search. So all data can be loaded on memory. That's my talk's assumption. Okay, so let us show me some real world use case, multimodal search. In this case, we have image like here. Then let's say we have clip image encoder, as all of us know. So we can extract image, feature vector from image. Then extract feature vector of image, extract. Then all of database images, we can extract feature vector, right? After that, given the text query, we can also extract the same dimensionality feature vector by using text image encoder. Then we can run search here. Then in this case, we can get this result. Then this is obviously a similar image, similar image. This text describe this one, right? So this is very basic multimodal search. So in this case, encoder determines the upper bound of like accuracy of the system. It's very simple. I mean, if we use much better encoder, then we can get better result. But this search part here, this search part determines the trade-off of the system: accuracy, runtime, memory. This is the thing. And here, this is another real-world use case. Again, this is, as you know, ChatGPT 3.5 was trained on 2021 actually. So there's a problem. If our question is like this, gold is asking for Olympic gold medals in 2022. So this is a future event from GPT. So if we ask this one, okay, GPT doesn't work, because GPT doesn't know the future event, right? So this is kind of problem of large language model. So training this ChatGPT is very time consuming, So what should we do? So what we can do is embedding. This is very, very popular recently. For example, in this case, so we have Wikipedia, and we crawl Wikipedia information, and we, like that divide into some small chunks. Then for each chunk, we extract feature vector again. Feature vector, feature vector. No. Then what should we do? We extract feature vector again for creative text as well. Then we done search. Okay, then we can get a result. In this case, we can get a list of 2022 Winter Olympic medal winner, blah, blah, blah. So it's almost answer, you know. After that, we can update the query result, query sentence by like this. Use the below articles, like use of this sentence is from this one, right? So we can directly put this to question sentence. Then we can ask ChatGPT. In this case, it works. So the thing here is ChatGPT part is fine, okay. So that's not our job. That's OpenAI's job, right? Fine. But how to put information in OpenAI? Oh, sorry, information to ChatGPT. Then the most easy one is like this. It's just search, you know. So this is a kind of, you need to know that, right? Because of everyone is discussing very, you know, clever, smart things, but the thing here is just search. Okay. And embedding plus nearest neighbor search is the current easiest way to provide knowledge to LLM. Okay. So here, if you see like tutorial of OpenAI, you know, there are many things about vector DB, you know, vector database. And let's use vector database, vector database. So what is vector database? You know, so that's kind of thing related to my talk. So I will explain this part a little bit. Okay, so I think this is kind of a useful, you know, category for technologies. You know, there are three levels of technologies, in my opinion: algorithm and library and service. Okay, for algorithm, this one. This is basically it's scientific paper, you know, and it's about mathematics. And often this is by researchers. Of course, this is a research paper, so by researchers. The famous one is, for example, product quantization, PQ. This was published in PAMI. Or HNSW, this is also a very popular algorithm. I will explain later. This is also PAMI. Or scan, this is Google's one. This is presented in ICML, right? Okay, so this is algorithm. After that, there is a library level. The library is an implementation of algorithm. This is usually these libraries provide a search function only, just search function. Then this is done by researcher or developers or something like that. So many kind of people try to do that. The famous one is of course face. I thought that is pronounced face, but Martin said it might be face. We don't know. We don't know. So it's kind of no one knows how to pronounce this one. Okay. Anyway, then NS leaf, so HNSW leaf or scan. So it's kind of you have ever heard of that, right? It's a kind of Python library. You can install them by pip or commander or something like that. After that, there's a service. For example, vector database. So vector database is, in my opinion, it's a library. I mean, search function plus something like handling metadata or serving, scaling, IO, or create, read, update, delete, CRUD, or something like that. It's kind of useful stuff. That is vector DB. And usually these things are by companies. Like recently, many startups companies are proposing many vector DB. Maybe famous one is Pinecone or Mirrorverse, or it's a kind of famous one. Okay, then what I want to say is this is actually one of the I want to say the most. So one library may implement multiple algorithms, obviously, right? So often people say like I benchmarked face. This is not correct actually. because face is the name of library, You cannot benchmark the library itself, right? So you should say that I benchmark PQ in face, then this is correct. So please follow this rule. Please don't say I benchmark face. That doesn't make sense. Okay. And this one algorithm may be implemented in multiple libraries. This is also obvious. Like this famous one, HNSW is implemented in by the original author to an MSD for these by original author. But Face team also have implemented HNSW. Okay, so one algorithm may be in many libraries. But often one library equal one algorithm. So in scan case, Google has a repository of scan. So this repository contains just one algorithm, I think, here. Okay. Then one service may use some libraries. So if I understand correctly, so Mirrorverse use Face and HNSW live inside, I think. Or sometimes re-implemented algorithm from scratch. For example, this vector VB8, these guys implement everything by Go. Go is programming language. So they use Go to re-implement HNSW from scratch, in my understanding. Okay, so these are kind of things, the wow. Okay, so in this talk, I mainly focus algorithm stuff. Okay. Okay, so this is a kind of wow of nearest neighbor search. There are million scale wow and billion scale wow. So this y-axis is n, the number of items. Okay, this slide is actually from my previous tutorial. I will explain. Today, my topic is this one, graph-based one. This is one of the million scale algorithms. Okay. For other million scale algorithms, you can see my previous tutorial, CVPR 2020. I explained very carefully. So for last 3 years, everyone using graph-based algorithms. So today I focus this one. The above part, billion scale part. So the Martin will explain. So in the next presentation. So let's wait. Okay, this is a big picture for today's talk. Okay, so the background is finished. So let's move to graph-based search. I first need to introduce how to construct a graph and how to do search. Okay, so graph-based search, it's a de facto standard algorithm if all data can be loaded on memory. And it's fast and it's accurate for real-world data. And it is important for billion scale situation as well, because graph-based search is a kind of building block of billion scale system. By the way, so why this one is fast? It's in my opinion, so no one knows. No one knows. The graph-based representation is somehow it's very kind of nicely captures the structure of data, so it's fast. But no one knows the real reason. That's my opinion. But anyways, it's fast, so we need to use that, right? So okay. Then the idea itself is simple. We can this blue dot is item vector, right? So this is query vector. Then so our task is to find this one, right? So we start from some random point, then we can hop, then we can reach this one. Hop means compare this green dot to some other dot, then we can move to some. But I will explain in detail next slide. So this algorithm seems intuitive, right? If you read papers and they are just saying like just beam search or something, but it's not so much easy to understand in my opinion. So I will explain. I will review the algorithm very carefully. Okay. The purpose of this tutorial is to make graph search not a black box. Okay, first I'll explain construction, how to make graph search, how to make graph. There are two approaches. The one is incremental approach, so putting item one by one. The second one is refinement approach. So we start from some graph and iteratively update that. So I will explain the increment approach first. Okay. Oh, by the way, all materials are already uploaded on our website. So please Google it, then you can download everything. Okay, so incremental approach. So let's say this graph. There are already graph, let's say. Then this is each node is a database vector. The blue one is a vector. For example, this one is x13. And this is the graph of x1 to x90, let's say. Okay, so in incremental approach, so our task is to add a new vector x91 to this graph. So how to do that? It's very simple. It's just create a new edges to neighbors. We can just we can run such algorithm here, then we can find similar blue nodes here. Then we can create edges. That's all. We can just putting and find new similar one and putting making edges. That's all. Okay. Then here, this is a new graph x1 to x91. Okay. The thing here is often we need to prune edges if some nodes have very too many edges. Because too many edges, then everything is okay.
Yeah, so how to define the edges? Yeah.
How to define the edges? I will explain maybe later. Okay. Then there are several strategies to prune that. Okay, this is also I will explain that. Okay. Okay, so that's the incremental approach. So another approach is refinement approach. That is iteratively refine an initial graph. That's kind of easy. It's starting from some edge, some graph. In this case, this is a random graph, I think, and we can refine it iteratively, like pruning or adding edges. In this algorithm, they first delete edges. After that, they put some long edge here. So if you see this one, it contains some strange long lines here, right? So this is a kind of thing. So the graph needs to be moderately sparse, moderately. So otherwise the graph is very dense. It means that the traverse is slow, search is slow. So, and some long edges are required for some shortcut. Maybe I will explain. Okay, so this is next I will show some search stuff. So this is one of the most, I use many times to create this slide. Okay, so how to do search? Let's name. Fine. Okay, let's name each node just for explanation. So A, B, C, D, E, F, G, something like that. Then is a query vector. Okay, so how to do search? So first, we prepare this candidate data structure. This is some array or some box. We put some candidate here, and the item inside here is automatically sorted. I will explain. Now, anyway, the important thing is there is a size limit. So the maximum number of items inside this candidate is 3. That's a definition. Okay. We start from some entry point. In this case, we decide entry point is M here. Here. Then we first record the distance to query. Query here, we can just simply take L2 distance, this guy and this guy. And the result is, let's say, 23.1. Then we put this information into here, candidate. So in this case, the current candidate is M, and this distance is 23. Okay, this is starting point. So let's start iterative search here. The first iteration. This is the iterative algorithm, so we run some iteration. Okay, so let's first pick up the unchecked best candidate. So check. I didn't explain check, so it's just remove that. So current best candidate is M, obviously, because we have only one candidate here, right? So this is the best one. So this is the best one. So let's start from here. So check it. Pick up best one and check it. In my slide, check means that this orange one, so this orange circle, this is check. We need to first check it. Then let's find the connected point from this check node. in this case, these there are 3 edges here. So these purple 3 circles, these guys are connected points. Then we call the distance to the query. In this case, this one and this one is 15, this one and this one 19, this one 11. So we compute distance here. Then put that in a candidate here, like this. Okay. So now candidate has 4 elements. And these guys are automatically sorted. So in this case, the best one is J. It has 11. J is here, right? This guy is most close to this one query. So it's here. Okay. Then it's fine. It's done. And I need to say that we need to maintain the candidate because the size is 3. Here there are 4 elements. So we need to delete the last one. Here. Then now delete it. So we have 3 candidates. So that's iteration. So our task is just to repeat this process. Okay. Okay, this is after the first iteration. Then let's move to the next second iteration. Okay, same thing. In this case, best one is this one. This one. Best one is J, meaning that this one is J. Check it. Check is orange. In this case, orange check. And this is previously checked one. So check means let's move to that one. So we can draw a red arrow here. Oh, and note that. So if we check this one, so we also check this candidate as well. So now there's an orange circle here. Okay. Then again, we find the connected points here. So J has many neighbors, so we can need to check all neighbors. Then compute distances. Then record it. And be careful that this guy has been already visited, in the first iteration, right? So we need to compute that. So we need a flag to check that actually, to save the computation. Okay. Then put that. So now we have a lot of candidates, here, a lot of candidates. So we need to delete many candidates here to keep the size 3. Okay, let's move. Then that's done. Then next to the third iteration. So we repeat the process. Let's quickly do that. Check this one. Best this one. Check this one. Connected components. Compute distance. Then put that and delete that. Delete. And next fourth iteration. This one best. Check it. And these are nearest one. In this case, so all of them are already visited. So let's skip everything. Then this is final iteration, I think. By the way, before sorry, moving a little bit. So in this case, after the fourth iteration, you can find that candidates, there are 3 candidates, but the best one and the third best one are already checked. Then fifth iteration. So remember that the definition of pickup is pickup the unchecked best candidate. So in this case, the first one is checked already. So let's pick up unchecked second one. So move this one, check and compute distance. Okay. Then there's a 4 elements. Delete this one. So there's a result. Then you will see that all candidates here have already been checked. Yellow, 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 right? The check. So that's this is a terminal, the end of the search. All candidates are checked, then finish the search. In this case, C is the most similar one to the query, obviously, right? This C is the closest, and C is the best one in this candidate. Okay, so that's a search process. You guys follow that? I created. I spent quite a lot of time to describe these things, so please enjoy. Anyway, okay. So the thing is, I want to say is you can get finally you can get 3 data structure you can obtain after search. The first one is obviously candidates. This one, so you can pick up the top K result here. So in this case, our size is 3, so you can get top 3 result.
What guide to determine the best size?
Okay, so how to decide the best size? This is a parameter, query parameter. So you decide, user decide. If you use use bigger value, then its search is accurate but slow. You know, if size is 1, then it's super fast, but the accuracy is not. Sorry, it's not fast. So it's an online parameter. No, there's no single best parameter for this size. Okay.
What do you decide on the stopping conditions?
Stopping condition, that's also a very nice question. There's in my opinion, there's no single rule. So many papers have many things, so I don't know actually. The one way is like this, or candidate check. That's one rule. So I use that here. Okay.
If you set the place to 1, are you guaranteed to find the single nearest neighbor or not?
Okay, that's also a very nice question. So it's the nearest neighbor can be found. It's guaranteed or not. It depends on the graph. If the graph is bad, then you cannot find that. Okay. Okay. Any other questions? Okay.
So is it because the search is greedy, but you cannot find the closest neighbor?
Okay. Yeah. Okay. Thank you. So yeah, you're right. So first of all, this is the approximate search and greedy search. So we cannot get global minimum. We can always get local minimum. That's first thing. That's first thing. And inside inside such approximated world, there are some many things. And in the worst case, some graph is very sparse. Then we cannot we cannot get local minimum. Okay. Any other questions? Okay, thank you for follow-up comments. Okay, what I said. So it's candidate. Then another output is checked item. This means search path. This red path. We know the checked item, so we can just create those kind of arrow things. This is also obvious. And the third thing is a visit flag. So for each item, we record visited or not. So it's kind of additional thing we can get if we want. That depends on the algorithm. Okay, this is search. Okay, so I introduced background and graph-based search basic stuff. Then I will introduce some observation from obtained from basic stuff. Okay. So first observation is runtime. So how to compute the runtime? Kind of theoretically. So the heavy part is that item comparison. Okay. Like this. I often say that how compute the distance between query and blue node, right? But this is all D of D operations, of course. This is D-dimensional nearest neighbor, D-dimensional L2 distance computation. This is OD. So if D is, for example, 1000, it's kind of, this part is dominant. So the number of this part, number of computation is this dominant factor. So the overall runtime is number of item comparison, right? And this guy can be approximated by length of search path times average out degree. Out degree is number of edges. So what does it mean? Let's see this example, this graph. Let's start with this one. So here, out degree equal 1, meaning that this guy is connected to this guy, just one edge here. So move here, right? So out degree equal 1. The next iteration. So for this node, there are two edges here. So out degree equal 2, right? Then move this one. Then here there are two edges. So out degree equal 2. So the overall item comparison is 3. 3 is the number of iteration, right? Number of length of search path is 3 times the sum of out degree divided by 3. So it's average out degree equal 5. So in total, 5 is number of this blue circle, purple circle. Okay. So I'm saying very easy, just because this is graph comparison. There's a number of item comparison is the dominant factor. Okay, so to accelerate the search, so how to shorten the search path? So how to shorten this red one? That is the one problem. Then another okay, so to do that, for example, long edge can be added with shortcut, or hierarchical structure can be used. And this one, how to make graphs fast. That is also the way to accelerate the search. So usually people delete redundant edges, right? Some edges are not useful, not important. So let's delete them. That's kind of strategy. Okay, the next one is a candidate size. So someone asked me already. So the candidate size is important factor. If size equal 1 here, that's greedy search. So let's consider this graph. That if size equal 1, this is just hot. So we stuck here. This is local minimum. You know, it's fast but slow. Sorry, it's fast but not accurate. If graph size, if the size is more than 1, it's called beam search. So in this case, since we are considering 2 more candidates, we can move to this one, and we can reach this one. So this is slow, but find a better solution. So here, in larger candidate size, better but slower result. And as I said, this is online parameters, so you can control this by putting integer here. And important thing is this is called EF parameter in HNSW. You know, if you guys have already used HNSWs, and it's, you know, the name of the parameter kind of not intuitive, right? But the thing is just this one, you know, just size, you know. Okay. Then pseudocode. that is my favorite side. Okay. All papers have totally different pseudocode, right? If you have read the graph paper, then they have all people have the search beam search code, right? And I put up some 3 papers that they're completely different, right? At the first glance, that's kind of problem. Why? The principles are very same, but the small details are different. So the hint here is why that kind of things happen. So it's because it explicitly states the data structure or not. That's the point, you know. So example here, the left one, they use array to represent a candidate, you know. So array, you know. So they need to sort that array explicitly, you know. But the candidate is expressed by a set here, you know. So in that case, they use when they need to sort, they just say closest point, you know. Or the third paper here, they explicitly use heap, meaning that probably it's true. You know that why why you know that it's surprising. Yeah, true. Candidates start in a heap, so it's automatically sorted. Good. And like checking stuff. So in this paper, they just say check, you know, just check. But here, the checking process is represented by a set, right? So it's different. And this paper visit in this code means check in our notation. So like notation is kind of different for each paper. And the check, visit, or something like that is very similar. So you will confuse. Okay. And the third one, let's say so visited item. Visited item is simply said to be visited here. So this implying that we need an additional hidden data structure. It's actually array, right here. But the third paper, this visited process is represented by a set. So it's kind of things. Okay. So and this is a termination condition. This is I received the question from the audience. So termination condition is totally different for each paper. So we need to be careful about that. So today's explanation is based on the first one, NGT, and I put some slight modification for simplicity. But that one. So generally speaking, my visualization is direct translation of this. Okay. So formal definition would be very helpful for everyone. So if some of you have, want to try, so please do that. Then let's create a standard pseudocode. That's very helpful. Okay. Okay, then I finished observation stuff. So next to move to properties of graph-based search. Okay, base graphs. So there are quite a lot of many graph algorithms, but there exists 4 base graphs. Basically, everyone do something for one of these graphs. These base graphs are slow and it's often very dense, so we need to update that. By the way, this slide are from this paper, 1VLDB 2021. This is super nice paper. This is excellent paper. So if you have, if there are author here, then please, I want to say hello to, because it's very nicely summarized survey paper. So please take a look at this one. I wanted to do that. I wanted to write this kind of paper, but my tutorial was accepted CVPR, and I read the paper and I found this one. Then also everything was here, so I have nothing to do here. Anyway, let's go. Okay, the principle here is that its graph should not be too dense. You know, if it's too dense, the search is slow for dense graph because we need to move it many times, right? But it should be moderately dense, because each point should be reachable. This is again some audience asking me question. If like some graph, if it's very sparse, then if item is isolated from the main graph, then we cannot reach this one, right? So that's not good. Okay, the first one is a Droney graph. This is famous Droney graph. This is some theoretical things here. We can always reach the correct answer, but it's almost free connected when D is large. So it's a kind of problem. So this guy is RNG graph. So relative neighborhood graph RNG. This is not famous in usual computer science, but it's very popular in graph-based search. So here, so let's consider X and Y. X and Y, right? Then let's consider room here. So definition of room is that consider this line and let's draw a circle by using this line. And the same thing here, draw a circle here. Then this overlapped area is room. And the definition is there are no points inside room. That's the definition. Just from this, it's not clear, but the conclusion is that this graph can cut off redundant edges. Okay, I will explain this later. This one is K nearest neighbor graph. So this is famous, right? And the good thing here is because we can limit the number of edges, right? Because this is K nearest neighbor, so we can set the maximum number K. Right? So it's fine. But this is no guarantee for the connectivity. So again, so some point might be isolated. The third one is minimum spanning tree. So this is famous. This is ensure the global connectivity, and this is low degree, right? This is a mathematical property, but this graph lacks of shortcuts. Okay, and this is a kind of list of graph-based methods. So it's quite a lot, quite a lot. So again, so this table is from this nice survey paper, and you can find some relationship of each method. No, it's too much. But the basic thing is that they are designing a good graph. That's the simple thing. That's all. Designing a good graph, then do the beam search. Okay. Okay, and some topics. The initial seed matters. It's kind of obvious, right? So let's compare these two cases. So start from here, then we can maybe hop here, 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 right? Or start from here. And in this case, we can hop just once, right? So good seed, obviously important. So starting from a good seed is it's shorter path, so faster search. But finding a good seed is also a nearest neighbor search problem, right? Of course. So it's it's hard. So usually some researchers propose this problem by small nearest neighbor search algorithm, weak nearest neighbor search algorithm, light weak nearest neighbor search, like tree or hash or LSH. Then we can get a good result, good seed, and then start main search. Okay, then I will explain some other things. This is edge selection strategies, RNG pruning. This is also very popular things, but I haven't seen visual explanation. So this is the first one, I think. So please study that. So here, let's say, okay, let's say how there are points, there are points here. Then we put A here. So how to create edges, that's our task here. one way is we can put all neighbors. We can maybe decide the maximum draw circle and all edges inside the circle. But in this case, it's too many edges. It could be quite a lot of edges, and that causes slow search. So it's a kind of not good. Or we can create top case search. Again, so in this case, just 3 here. It seems good, but in this case, these guys are not reachable. So it's again leads low accuracy. So this one is good. So this one is good, and the thing here is from this A. So this one is okay, but this one is we don't need edge here because maybe these guys connected to each other to B. We don't know in terms of A, from the view of A, but anyway, we can just write one edge here. The same thing happened, one edge, one edge. So this is our energy pruning. Now we can preserve a moderate number of edges. Okay.
It's not likely that you may lose the vital information if you don't put a relevant edge.
You mean, it's not clear to me. Could you say it again?
Because you said, this one said we don't need this edge.
Mhm.
I think this edge is vital and we skip it.
You mean skip the computation for that?
No, you said, yeah, somehow, and you said we don't need this edge. So is there anything to guide us to remember a certain when we need an edge and when we don't need it?
Maybe I'm still not clear. But then the next slide, I will explain some way to do that. So sorry for that. Okay. Okay, so edge selection strategy. So the now problem is like this. So there are B, C, D, A here. B, C, D, A. And putting A. So given A, how to make edges to B, C, D, E. So which one should we select? That's the problem. So let's start. Let's find the nearest one to A. Anyway, in this case, C is nearest to A. So let's make it. Here, this is a rule. For all neighbors of A, we compare red arrow and green arrow. If red arrow is the shortest, make an edge. This is a rule. Okay. So here, this time there are no neighbors of A. Neighbors meaning that they are connected by edges. So in this case, A is nothing. A has no neighbors. So we can just create edge anyway. So this is first step. So it means that the closest one gets put edge. That's all. Okay, that's the first iteration. Okay, this is done. Then let's move to the next iteration. So this guy is the second nearest to A. So let's consider this one. Then let's apply this rule for all neighbors of A, meaning that green one. In this case, A's neighbor is C. So let's consider this one. Then compare red arrow and green arrow. The red arrow is B and A. The green arrow is B and C. Compare these guys. And if red one is the shortest, then make edge. Okay. Here, green one is much shorter, right? So we don't make edge. Okay. Okay. It's just an operation. Just to follow this rule. It means that we have C. We have C, and B is very close to C, so we don't need to create an edge. That's all. Okay. Okay. Done. The next one. D. This guy is the third nearest. Then let's consider this rule. Then in this case, A is shortest. AD is shortest. So let's make edge.
So we also calculate the distance between C and D as well.
C and D, yes, C and D as well. Right. Then a good point. So it's heavy. Computational cost is heavy. Okay. The next one is E. This guy, fourth nearest neighbor. Then in this case, a green one is for all neighbors of A, meaning that D and C, and there are 2 green arrows. And in this case, this one is shortest, so we don't make edge. Okay. Okay. not to make any. So this is done. So finally we can create a H, C, and D. It seems good, right? Because B, C, D, E already seems like too much, you know. Just 2 seems fine. So this is done. Okay. So this R energy pruning is known. It's efficient. But the point is, this is implementation is easy. You can just follow it. You know. The bad point is it's require many distance computation. Okay. Okay. So the time is limited. So let's move to representative works. So hierarchical nearest navigable small world HNSW. This is one of the most famous one. Maybe you think graph-based search means that HNSW, right? So we construct the graph hierarchically and fix the number of edge per node by our energy pruning. So this is not dense because for given node, so the number of edges is kind of fixed by our energy pruning. So it's very it works very well for real world, and it's like hierarchical stuff. So it's good. And this is used in various services like Milbus, VB8, QD, and Graduate. So all of these stuff, they use HNSW inside. So it's very, very stable algorithm. And there are 3 famous implementations. So first one is from the original authors. The second one is lightweight implementation by the same authors. So the first 2 are similar. And the third one is phase 1, is re-implemented version. Okay, and this is kind of interesting. So it's like discussion in on the Facebook user forum in Facebook. It's kind of old, 3 years old. So the content may be different, kind of old. But I asked the original author Yuri, so what is the difference between these 3 implementations? And he explained quite a lot. So if you have time, so please read it later. Yeah. I guess these algorithms, these all vector database stuff are using one of implementation from these 3, I think. So these 3 implementations are important. Okay. Then okay. For HNSW, there are many good blog posts here. So please take a look at this one. That's also first I try to do that. So I will try to explain HNSW very carefully, but I found that there are good blog posts. So I put just a link here. Okay. And this is NSG, navigating spreading out graph. This is called monotonic RNG. So in some cases, this graph is slightly better than HNSW. Okay, so let's move a little bit fast. And what I want to say is this NSG is implemented in face as well. This is not so much people know that. But so if you want to use face, if you are using face HNSW and you need a little bit more accuracy, then please try this one. You can just change here, here HNSW to NSD. Then parameters are similar. Okay. That's kind of you can try. And NGT, this is also another kind of algorithm. So one thing is this is currently one of the best methods in the benchmark. So please take a look at this one. Okay, and the disk ANN Vamana. This is also graph-based search algorithm. This is from MSR India team. What I want to say is they extend this algorithm to interesting setting, the data update setting or filter setting, and they extend the flash disk ANN, filter disk ANN, kind of an interesting extension. So it's an active group. Finally, I show some discussion. Okay, so this is kind of very interesting things you want to know. So just nearest neighbor search or vector database. Okay. And vector database companies are saying vector DB is cool, you know, it's kind of because they are selling vector database. So, but my own idea is obviously let's first try the simplest NumPy only search. You know, just you can implement that. Then 90%, in my opinion, so it's fine enough. You know, just NumPy is enough. And if it is slow, you know, runtime is the only concern for you. Then you can use face nearest neighbor search algorithm. It's fast than done, right? So when you need vector DB, that's there are some problem other than speed, you know, like up to date stuff or delete stuff or something like that. Then you need to use vector DB. Okay, this kind of simple diagram. And which vector DB is good? I have no idea about that. So they are fighting each other, you know. So please try. Okay. But if you need a clean and well-designed API, then I recommend taking a look at Docker Array in Gina AI. So the third speaker, Han, he's creating interesting library. So please take a look at that one. Okay, and these are some useful resources. I don't know the reason, but many vector DB companies have their own blog, and that blog are very nice. So why? I don't know, but please take a look at that one. And okay, this is the final slide. So the progress in the last 3 years. So 3 years ago, I did some tutorial. I did CVPR 2020. So after that, what happens? So my opinion is that, so interestingly, the basic framework is very same still. So people using HNSW or IBFPQ, they are baseline. So it's kind of it's same. And HNSW is still de facto standard. So it's strong. So although many papers claim, our method is better than HNSW. But still, HNSW is good. And disk-based systems are getting attention. So some of people, try much more bigger data set. And as I often say, as I say many times, the vector DB has gained rapid popularity for LLM application. This is good. That is good for we nearest neighbor search guys. We are doing. So nearest neighbor search. People say that previously people said that nearest neighbor search is just search, so it's not interesting, kind of. But now we can say that there's a vector database, so we are doing some interesting state of the things. Right? So it's kind of a good thing. But anyway, but for us, interesting thing is that here, the D, D was previously it's around 100. If it's much more, then do PCA, dimensional reduction, then you can get 100 dimensional vectors. That's fine, right? But now, OpenAI API provide 1000 D, so we cannot do PCA, right? So we need to consider D equal 1000. D 1001. That's now we are living, This is not so much easy, This 10 times difference is not the same as 10 times difference of the number of items. So D is a very important factor. So again, something like that. And the GPU NN is powerful, but it's less widespread than I expected. And I thought that everyone used GPU, but now not so much. GPUs are still powerful because of vector DB. Or anyway, CPU is cheap. And there are two competitions, so CSAP competition and BKN benchmark competition. Competition, and maybe next time, Martin will explain another one. Okay. And there are new billion scale data set. And in my opinion, so graph-based search is kind of immature. So breakthrough algorithm that goes beyond the graph search based sort is awaiting. Okay, okay, this is the end of my talk. This is reference. Okay, thank you. Do you guys have questions? Okay, go ahead.
Is there any work on you have query pattern data from other input? Let's say you can use query behavioral data for the last 6 days to optimize the structure so that the most popular queries the shortest path.
That's a very interesting question. So if we can obtain the query sets, can we use that information to enhance the performance? It's maybe it's an ongoing research. So it's kind of many people are trying to something like that. But current libraries, they don't support that usually. Benchmark, yeah, there's currently no benchmark in my opinion. Okay. Any other questions? Quick questions? Okay, so let's take one minute break.
We can also take 5 minutes.
5 minutes. Okay, so
5 minutes, so we start at 35.
Okay, 35, starting from 35. Okay. Okay, let's move this one to here. Okay, thank you.
We can also get some. Yeah. Maybe let me just share my screen.
Yeah, I will stop that. Yeah. No, I don't need to stop that. No.
And I think you need to told me that you have to reshare you have to stop sharing.
No, you can.
Let me see. Yeah, not support. Not support.
Yeah, wait.
What can you see now on your screen?
Yeah.
I share.
I know.
I'm still too big.
Yes. No, that's it. Listen, right? Oh yeah, it's surprising. Like great animations.
Okay,
I think no one. Yeah, I really encourage one. I have no time, so we could do. I have small kids now, 3 years old. So I have no time. So I meet them after my day. Great. For no, yeah. So let's like some fun, like. Could be the de facto standard explanation. This is what it's actually. What is the thing I'm saying? This one? It's a transcription. All right, it's 35. Let's continue. This is the second part. My name is Martin. I'm going to talk about billion scale nearest neighbor search. And you saw this in the beginning. So just to recap, what's the pipeline here? The pipeline is that we have n vectors. Now n is going to be 1 billion. We want to first build an index. We're going to see this is going to take several hours. Then we want to do the search. And the search is, well, you take a query, you ask your index for candidates, and then you scan through these candidates and you return the closest point that you get. Let's first maybe put something into perspective that Juske said, and this is like how fast are algorithms these days on a million scale. So this is from ANN benchmarks. I'm co-organizing like this benchmarking suite. We do million scale ANN benchmarks. And this is 1 million vectors. They come from graph word embeddings. So this is like word similarity search. And what you see first is probably that there are many implementations that can solve this. If you ask like now, we heard about graphs, where are the graphs? All of those are graph-based. 5 years ago, almost nothing was graph-based. Nowadays, all of them are graph-based. They are sorted by performance, and you see the graph-based one on top. Right. So what Juske told you is like the state of the art when it comes to performance, query performance. And what you're going to see here is on the x-axis is quality, it's recall, like how precise was the nearest neighbor search query on average, how many true nearest neighbors were returned. And this is, we now started to use this log at scale because they are so precise. We call it approximate nearest neighbor search. But if you look all the way down there, it's, so this here is 50% correct. This is 90% correct. This is 99% correct. This is 99.9% correct. All of the queries, and you still get really good performance. There are many implementations available that give you more than 1,000 queries per second on a single thread. There's a huge plethora of different algorithms. And then there's this question like also where are the vector DBs? All of them are vector DB implementations. You see actually the most performant ones, they are not part of vector DB yet. Like this was the NGT that Juske told you on one of the last slides. So this is how million scale nearest neighbor search looks these days. Now, we want to go to billion scale. We just want to do this 1,000 times larger. And our rules for ANN benchmarks million scale is, well, you have to do the index building, the searching single threaded, and you get 2 hours to complete the run. After 2 hours, we just kill the container. You're not going to appear up there in the results. And one of the participants, I think like two months ago, asked, well, could you relax these 2 hours, maybe to 24 hours, then we can do even better. But if we think now we want to scale all of these things up by a factor of 1,000. So these 2 hours are already 2,000 hours. If we assume like an unrealistic scaling that it's 1,000 times larger, it's probably going to take 1,000 times longer, which is not true, I'm going to tell you. But this would mean 83 days index building. The one in the bottom, like the proposal here that we did not accept, would mean it takes 3 years to build the index. Just to put these things now into context, because it's going to be important for this talk, how much time is spent in these 2 hours on index building, how much time is spent on searching. Like some of the algorithms spend an hour, 55 minutes on this part. And then in 5 minutes, they just ran through all of their hyperparameters, because a single run for them takes a second or 10 seconds or something. So there's a huge unbalance between how long it takes to build the index and how long it takes to answer these queries. So what we did in 2021 at NeurIPS is we started this challenge, because this was the picture before. You have this huge set of algorithms that can do million scale nearest neighbor search. Then we created one baseline for billion scale nearest neighbor search. Then we ask, please compete in our competition. There were 3 different tracks. Those are now the results from only one track, which was the in-memory track. But many people like signed up for doing this competition. At the end of the day, we got 3 teams that actually were able to finish the task. And there were not many improvements upon this baseline. And this is not like 30 implementations now. So for billion scale, there's single implementations that can do it. It's still like this today. And what I'm going to tell you at the very end of my part is, like nowadays in 2023, there's one new competitor. Yeah, only one that can do kind of improves on our picture here. But it's something that not many people can do. Okay, what's the too long did not listen of this talk? So we do billion scale nearest neighbor search. I'm going to tell you about 4 different settings. Well, first of all, you have to ask yourself, can you store all of the data and your index in RAM? If you can, well, then do you aim for high recall or not? And then there are different choices. If you cannot store data and index in RAM, you can still aim for high recall, good quality, but then you have to do certain other tricks. I'm going to start at the very bottom, at the very top, then I'm going to go to the very bottom, but we learn a lot from the top events that we can then just apply for the ones in the bottom when we run out of memory. What I do not consider here is non-CPU architectures, no GPUs, no other things. I don't talk about different queries. I want to solve nearest neighbor search queries. There are no range queries, there are no filters. I also don't care here about adding, removing, the thing that Yusuke said at the very end of his talk. Those are interesting research topics. I'm going to come back to them at the very end of my presentation. So first of all, if you're interested in billion scale nearest neighbor search, one of the NeurIPS things that we did in this NeurIPS competition actually was sourcing data sets. Because before this competition in 2021, there was this big ANN data set. It's these old SIFT image descriptors. This was a billion scale data set and nothing else basically existed. It was a challenge. So what we did is we released 5 other data sets with this challenge. And just to give you an idea now, what kind of size are we talking about? Just storing the raw vectors is for Facebook, the SIM search net++, which is some copy detection image descriptors. This is like just 256 gigabytes, somewhere on your disk, just the raw images. The biggest data set that we have is this Yandex text to image. That's 800 gigabytes just on your disk. What we want to do is we want to do nearest neighbor search on this scale. All right. And we start by doing it by having really good machines. Like we talk about, like we have some multi-socket Xeons. I'm going to tell you a little bit about that in more detail in a bit. We have hundreds of gigabytes or terabytes of RAM. So we say like probably we can store both data and the index in memory. What I claim the best thing to do is to build a graph. But actually a lot of things happened just during the last months or last year with these graphs, so it's still going to be a bit interesting. So I'm in the same situation that Yusuke was in, that when we got accepted to CVPR, I felt like I have to do a lot of work. But very luckily, this paper here appeared a month ago and has as the topic scaling graph-based approximate nearest neighbor search to billion-sized data sets. And all of the plots you're going to see are from this paper. It's an excellent paper. It's not yet peer-reviewed, but I'm going to tell you a little bit about some maybe shortcomings, but it's an excellent paper. Just to tell you a little bit about what kind of machinery they used, what does high resource mean? They use 2 different setups from the Azure cloud. And it's a 4-socket Xeon, 192 virtual CPUs, 2 terabytes of RAM. I checked it yesterday. If you want to rent it, it's a 384 USD per day. The smaller one is a 2-socket Xeon, 96 CPUs, 672 gigabytes of RAM. This will only cost you $144 a day. For me, being an academic, those are huge numbers. Your impression might vary. So how much money are we going to spend building our index for on a billion scale? But first, we have to understand what are we going to do. The short message is that luckily, when we talk about graphs and we do certain optimizations, the things that Yusuke told you a few minutes ago are still the same things that apply on a billion scale. So what are these graph-based approaches? All of you are now experts in that if you joined Yusuke's part. So we have our billion vectors. They are these nodes here. And they are connected to this diverse set of similar points with some long-range edges, which were like the result of this pruning. And then we do this incremental build. So we use the search algorithm to find potential candidate neighbors, and then we prune these candidates. That's how we build these graphs. Now, what Yusuke didn't need to go into detail about is how much space is this going to cost, right? Because on a million scale, it's usually not a problem. On a billion scale, it's a huge problem, because what's the index size going to be? well, you have 1 billion of these nodes, and then you have to ask what's the average degree of a node. And this is roughly going to be your index size. And as Yusuke told you before, this is something that you get no help with. You have to set it yourself. But at least you can apply some thinking to make sense of these numbers. I'm going to tell you about this in 2 slides. How do we get faster build times? Well, we could try to make these graphs more sparse. That would help. In particular, Yusuke told you about this beam width. Like if you search for points, how many candidates are you going to store? Reducing this is greatly going to help. But if you do so, you might end up with much worse graphs after this building process. Then there are some trade-offs, because if you build a much worse graph, then you need a larger beam width when you search. And in that point in time, you have to ask yourself, was it worth the effort spending more time in the index building, or was it worth to actually save time on the index building part? I'm going to show you some numbers in 2 slides or so. All right. The only thing that people basically did now going from million scale to billion scale is they had to think about, well, this insertion of a single point, how can we parallelize that one? And let's just recap how did we insert a point into our graph. Yusuke told you in slow motion. I'm going to do it a little bit faster. So you carry out this, so you have your point here that you want to insert. You start somewhere, and then you carry out some kind of 3D search. You visit some nodes, you stop at a certain point, then you prune your edges, and then maybe this is what you end up with. This was the insertion of a single point. Now let's say we have our 200 CPUs. They all should work on this in parallel. There is a huge problem here when doing this, because we have this degree node, and the problem is not so much what we do on this single node when we add edges. The problem is this node here received a new edge, and it could be that this node now is above its target, the maximum allowed edges, so you have to prune it. Now comes the problem is there are like 200 of these threads doing this in parallel. Could it not be that this node over here also connected? And then you have all of these funny race conditions. Okay, so what you can do and what people did in the literature is you use this prefix doubling. So what you do is you don't just do insertions one by one, and you put logs around all of these situations where you run into a problem, a potential problem. Over here. What you do is you split it up a little bit. You say, first, I'm going to look at some nodes, I'm going to do the search. Then I'm going to see what did all of these nodes, now all of these insertions add for edges. And then in the second round, you go through these edges and you prune them in this part. So you split up this pruning part into, first you insert, you do this in parallel, you add these edges, then comes the pruning part in the second part, and you also do this in parallel. Okay, and this is almost the whole story. Going billion scale for a graph, you have to think about how to do these insertions. And if you do them carefully, you actually get almost perfect speed up according to the threads. Okay, now there's one big problem, and I want to go a little bit into that now, is on a billion scale, you really have to understand what you do. You've seen like Yusuke telling you, well, there's no good rule for this, there's no good rule for that, and it applies even more if you do these things on a billion scale. So let's just recap. When we build our index, what we have is we have a target degree for our graph. This is the R parameter. We have the candidate size, this beam width, and then we have some pruning factor. When we search, we only have one parameter, what's the candidate size during the search. Okay, now Yusuke already told you, but just to see it also written in the paper, for this KNN, which is not HNSW, but closely related. What they found in their experiments is that there is no single parameter setting that is optimal for all recall regimes. There were significant trade-offs in the other recall values when you maximize for recall above 0.99, so they chose some values. This doesn't help you so much. What I want to highlight is there's another paper, I'm going to talk about this paper at the very end, which claims to have a new good approach. They take the very same implementation. They also take the disk ANN. They call it here different, but the manner because of there's the implementation, it's disk ANN, and there's the idea, it's the manner. And what they say is, and they are also experts in the area, what they say is this, the manner, which is disk ANN, well, they couldn't even do it for 25 gigabytes data sets. We want to do billion scale, 40 times larger. They couldn't do it for 25 gigabytes. For a 100 gigabyte data set, they needed like 1.4 terabyte memory. And then you're still a factor 10 away. They also say down there, it's difficult to read, that for 25 gigabytes, this took them already more than 7 hours. How is this ever gonna finish? And it kind of makes you wonder, like, how can it be that, I'm gonna show you on the next slide, the results that the people on top, they easily build the index. The people in the bottom say it's impossible to build the index. And it's again, what Yusuke told you is, here the problem is really, they say, we use this disk ANN implementation, but they tell you no details. You have no idea how they built this graph. The only thing you heard is they probably chose some parameters that did not work well. Let me show you some parameters just to answer the question, like how long does it not take to build data indexes on a billion scale? So what they did in this paper is, now there are some details that might be not so important, but there are 4 different data sets that they have used. And they try to be really concise, which is super nice in their parameter selection. So 64 here means that each node was allowed to connect to 64 other neighbors. 128 means what Yusuke told you about the candidate set size during the search. This was set to 128. Then there is an alpha for the second round of the pruning, doesn't matter so much. The good thing is, with these parameters, you actually have a good idea how big the index is going to be, because the index is going to be, well, you have 64 neighbors. And to store this edge, you just have to store like what's the index of the other node. So you need like 4 bytes, even on a billion scale, to identify this. So this 4R index is going to be 256 gigabytes for these 3 data sets. It's going to be 600 gigabytes for their choice over here. So you see tiny changes in these values mean a lot with regard to the index that you're going to build. Is it now easy to understand how these parameters are going to influence the build time? Unfortunately, not at all. This big ANN data, so all of them are billion scale. This one here has 100 dimensions. No, this one has 128 dimensions. This one has 100 dimensions. It's much lower dimensionality. Still, when they run, they're, okay, first things first. How long did it take them to build the index? The answer is 11 hours. Right, so we are not like in multi-day things. We are not in years. You can do it in 11 hours. When you go back to the machinery that you've rented, this will cost you like $200 US. Then you have the index. You can store it somewhere. You can reuse it later if you want. Right? It's not going to be, it's possible to do this on a billion scale. It's completely unclear, and it's very algorithm dependent, how build times are going to react to certain things in the data set. So if we look at this, this is higher dimensionality. We go from 11 hours to 15 hours for one implementation. Actually, for HNSW, the other implementation, you go from 9 hours down to 6 hours. Like you would think like they should behave in the same way, that one of the data sets is just more difficult to index, right? And that's why it takes longer. But these individual strategies, they make a huge difference. And it's really difficult to predict these running times. How does it scale? So if you increase the dataset size by 10, so here we are at 1 million, then 10 million, then 100 million, then actually 8 billion. A 10 times increase is going to be around 11 to 12 times increase in build time, which is actually pretty nice. So it's almost linear scaling. Right? If you were now to ask, how will 10 billion, storing 10 billion points, how long is this going to take? Probably you are then in the hundreds of hours, right? But it's kind of predictable.
So a question about
Yes.
how the algorithm completely deterministic? Because I think that the speaker spoke about from initial condition that influence the algorithm.
Right. So the question is, are the algorithms deterministic? And now there are a lot of them here on the slide, right? Let's start with HNSW. HNSW has this multi-layer approach. If a node is inserted, you pick the level where it starts. So there's randomness there. This KNN, you start with a random k-regular graph. It's random there. So it's a bit, maybe you think it's a bit fishy to see a single value.
Yes, on single run, how sensitive it is to that.
I actually don't know. And I think no one said it in the literature. If you were to do this 100 times and you put error bars around it, how sensitive it is. My guess is it's almost, like there's almost no difference. All right. So with graphs, you have kind of a good idea how the index size is going to be, because all of them make you set this maximum index size deterministic as a user set parameter. You won't have a good idea how long this is going to take, right? But you can do it here in the tens of hours. This is building, and this is the scaling. Now, almost neglected, but because it just doesn't have so many problems, is what about search now? So usually now in this setting, you have 200 CPUs, you have 100,000 queries. What do? You just batch them up, and you give them to the threads, and they work on their part of the batch. And it's usually, it's almost, there are almost no logs here because you don't change the graph. Yeah, so this works pretty well. And the only thing that you have to set, as Yusuke said, is what kind of candidate size are you going to use in the search? And this is a little bit trial and error. Like the higher, the better, but the slower it's going to be. The scaling is, I think, amazing. Like, let's not discuss the picture too much, this plot too much to detail. The giveaway message here is your data set is 1,000 times larger. How much slower is the query going to be? It's like 2 times slower. Yeah, it's 1,000 times larger, but it's only 2 times slower to actually answer the query. Although you had 1,000 more factor 1,000 more points in it. All right. So this is the summary. Why are graphs so good? And they have this very interesting plot in their paper about the number of distance comparisons carried out. So you heard about during the search, you do these distance comparisons. So it's good to know how many distance comparisons did you actually carry out. And graphs are just really, really good at making a small amount of distance comparisons. Here in this graph, what you see is you see some graph-based algorithms. Those are the ones down here. And they are compared to IVF-based algorithms that I'm going to explain in a minute. They are the ones up there. And if you look at how many points are inspected, it's just crazy how little they need to see from the data set. Let's try to make sense out of this plot, because I think it's very important. So here the data set size is 1 million. This data point says that to get recall above 80%, they did 10,000 distance comparisons. What it means, they looked at 1% of the data set. Now the scaling here looks pretty bad, right? But it's actually kind of because of double logarithmic scale. On a billion scale data set, they achieved the same by only looking at 0.01% of the data set. So a tiny amount of the data set is enough to go to get high quality results. Yes.
Explain a little bit of what it means to have 80%.
This here is over 100,000 queries. On average, they found above 8 out of 10 true nearest neighbors. So the recall is here. They returned 10 nearest neighbors. How many of them? What's the fraction that were actually true nearest neighbors? So this means on average, it's above 80%. And they do this by looking at 0.01% of the data set. Graphs achieve this by looking at 0.0001% of the data set. This is 1,000 points on an index that actually contains 1 billion data points. This is what they are really good at. What are they bad at? The influence of the parameter choices are really difficult to predict. Yeah, so you saw these parameter choices over here. Can you get a good estimate on the runtime? Probably not. The best idea is run it on a smaller data set and assume that it's almost going to be almost linear. The index building times are pretty high compared to other approaches. Right. If you want to get started, so here I talked about a little bit about DiskANN. I think DiskANN, this is from NURBS 2019. The good thing is now this is from Microsoft, and this is now a team of 20 or 30 engineers that work on this library, right? And I'm going to go back at the end of the talk talking a little bit about other things they can do. But you can, this is a Docker file for installing it. This is a Docker file for running billion scale nearest neighbor search. I'm going to put it on the website material as well. All they ask you to do is you have to know what's the size of the beam, what's the beam width when you build it, what's the degree going to be, and when you query, what beam width are you going to use there? Yeah, so all of the hard part is actually on you. But the code here is pretty nice. Right, that's all I wanted to say about graphs in this. Any questions? Sure.
Are there any distributed algorithms?
So the question is, are there distributed algorithms?
Yeah.
Yes, so there are. So what you usually do, but like I would say FIS is the better library for this, for doing this. There you have there are wiki pages that explain what you could do. For DiskANN also, I wanted to say this at the end, but DiskANN is used by Microsoft in their Bing search, right? So they index trillion points using this approach. But then they split up these trillion points into shares of billion scale, and then they use rather small machinery for this billion scale. But then they have this problem that they have to merge at the end. So they use this distributed approach, but you won't find it here. You have to implement it yourself. Yeah.
So these indices, when you store them in disk, are they ordered in any way?
I'm gonna come back to this question in like, yes, I'm gonna tell you a little bit about this in 15 minutes. Yes, so the question was how to order this, how to store them on disk. Right. Something that I really want to explain to you, because many of you might have used this already, is what do you do in a regime where maybe, I mean, this is more of a path into the lower bottom where you have to do something where you can't store all of the vectors. But this is still going to be interesting by its own. So there are IVF-based approaches, and IVF is this inverted file index. You also build an index, and these indices are usually much easier to understand. So I really want to explain them to you. You have your billion points over here, and it goes in 2 steps. First, you train a partition, either on these billion vectors or on a smaller subset. Finding a space partition, it's usually cluster-based. You could also use locality-sensitive hashing or something for this, but clustering-based is empirically the better choice. So you run k-means with k set to a certain value that we can discuss in a bit. out come k centroids. What is then the data structure going to be? With each centroid, with each partition here, you're going to associate a list of potential points. How do you insert a point? Well, you do the kind of obvious thing of, you look, where is the point? Let's say it's over here. Then you associate it with its closest centroid and you put it in this list. X1 goes here. This is how you build the index. The index is then the centroids and all of these lists. One build parameter. How many clusters do you want? Searching. As you find your nearest, how do you find the nearest vector? Well, you take your query vector, you look, oops, you look, where is it? Might be over here. Let's say this is your query vector. What you're gonna do then is you go to your closest centroid. With it is associated a list, and you go through all of these elements and compare them and return the closest points. This is often not good enough. So what you have to do is you also have to go to other close centroids. For example, maybe this here is also not so far away. So you would also go to this list and also check those. Much easier to understand, in my opinion. How many points are you gonna inspect? Well, how many clusters did you want to expect, and what's the average cluster size? This is how many points are you gonna expect on average. And again, as mostly happening in nearest neighbor search, this number here, number of clusters inspected, this is on you. You have to say how many clusters you want to inspect. How do you choose parameters? The back of the envelope calculation is just you take the square root of your dataset size. You can also approach it differently and say, well, look, I know these graph-based algorithms, they can do it with 0.0001% of the data set. I want to do the same. So they look at 1,000 points. To get this granularity, I have to have 1,000 points in my cluster. Now I am on a billion scale. Now, unfortunately, need millions of clusters. When you're in this situation, it's kind of strange, because now comes your search. And first you have to find your, let's say, 60 nearest centroids. So you have to solve a million scale nearest neighbor search problem to find out where in which parts to look. To make this practical, what you usually do is you build an index on top of the centroids. So the often and the standard way for FIs to do it is you build an HNSW index on the centroids. And then you use the result of that search to guide which lists to look into. Another approach, it's one primarily used also by Google in their scan implementation, is that you have a hierarchical k-means. Cluster in 1,000 points, 1,000 centroids, and then each of these clusters are again clustered in 1,000 clusters. It's also a way to split up your data set. It's much faster to train. All right, what are advantages here? You get a very predictable index size. Yeah, it's just centroids plus the number of points, a tiny index. You have super strong implementations for FIs. It's even, this is an approach that works well on GPUs as well, if you have the capabilities. Disadvantages are really, you need to look at a lot of points to get good recall. So this is something that I wouldn't put at the high recall regime. You have to be able to, like, if you are happy when you return 60% of nearest neighbors, or 70 or 80, then you can also use that. And since you have to do that many distance comparisons, you also have to speed them up. For graphs, like Yusuke didn't have to explain anything about quantization. For these IVF approaches, you're really bound by how many points did I inspect here? How many distance computations did I carry out? Okay, how to get started? It's on the slides. With FIs, it's much more straightforward to do these things. All right, last part I want to discuss is, what if you don't have 2 terabytes of RAM available, but you have, let's say, 64 gigabytes of RAM? If you are below 64 gigabytes of RAM, might be difficult, right? But you can do billion scale search easily when you have 64 gigabytes of RAM available. And how does this work? First, we have to understand something, and that is how do we compress vectors. And I'm going to explain this a little bit, and it's I'm actually going to use slides from USkill's 2020 tutorial, and then we put it all together. So just to recap what the problem now is you have 800 gigabytes is your data set size, but you only have 64 gigabytes of RAM. Yeah, there's no way that you can store like the data set in some way on the disk. You have to do something clever. And the clever thing to do, and it's clever for many, many reasons, is that you compress the vectors. Quantization is the compression technique. And it's also, you have to be able to understand what's going on, because paper is like just going to tell you, this is what we did. And so the whole story is, this evaluation paper also included FICE. And they just tell you, I mean, for graph-based approaches, they told you that. And hopefully it makes sense after Yusuke's explanation what these parameters mean. For FICE, they say, well, it's like an IVF. And here's a nice string. If you understand the string, you kind of know what we did. If you don't understand the string, you have no idea what's going on. The thing you might be able to understand now is the thing in the middle. It's IVF on what is 2 to the 20 many centroids, and you build an HNSW index on top of that. So that's the basic data structure, is this IVF clustering approach that I explained to you. But they do something before, and they do something after this, and it's really important to do these things. So let me try to explain what's going on here. So the basic idea behind quantization is that you have your original vectors. They use a lot of space, let's say 512 gigabytes. You want to convert them such that each vector is represented by a very small code. Maybe you can do this with 4 bytes, 32 bits. Then you could store a billion scale data set just in 4 gigabytes of RAM. It would be really nice if we could run the search on these codes down here. What kind of code do we want? Well, we do this transformation. At the end of the day, we still have to be able to say, what is the distance between these 2 points? And we want to be able to do it from the code alone, without looking at the original vector. Shouldn't be too difficult, you know, and like in data compression, sometimes it's really difficult to decode them. That's not what we want. We want to do a really quick distance computation. And the distance that we see here in code space should have something to do with the distance that we saw with the original vectors. This would be really nice as well. At the end of the day, these codes, they shouldn't be as long as the original vectors. Then we didn't learn anything, right? So they should really be smaller. Okay. What are ways to do this? Many of you have probably seen like just use like 16-bit floating point values instead of 32-bit. This is probably going to speed up your application. You can do things like scalar quantization. You have a min, you have a max range that you know of your values. You can just split them up into buckets. Like here, I split up 0 to 3 into 6 different parts. So this 0.54 would be the first part, and so on. You can still recover distances because you kind of know where the original vectors were. You could apply hashing, but the best approach so far is that you use product quantization to do this. How does product quantization work? It's different to the other approaches in the following sense. So what you do is you have your vector. And here in the example, it's 6-dimensional. And we want to reduce this dimensionality to only be 3-dimensional. And those shouldn't be floating points. At the end of the day, they should somehow be shorter. So what you do is you have your original dimensionality, you have your target dimensionality, you make blocks of the same size. So this is then the first subspace is colored in red, the second subspace is in blue, the third subspace is in green. What you can now do is you can, for example, run k-means on these lower dimensional vectors here. Maybe it's all of your training data, maybe it's only part of it. what you get out, and you run k-means with a very small k now. So before we were in the millions. Now let's say it's 256 centroids. So now what we can do to encode these two values here is that we just find the nearest centroid again. Let's say it's this one. Those values are very close. And then what you store is just the ID of the centroid. So you just store 2. That's the first entry. You do the same for blue. You do the same for the green part. What is the product quantized version of X? It's this X bar. It has 3 small integers. These integers are so small, they're only a single byte. It's kind of simple to do. It's memory efficient. And you can also estimate the distance, as I'm going to show you. So why is it memory efficient? And those are things that you often set yourself. Well, if D is large, for example, 128, and you had 32-bit floating point values, you get like 4 kilobits was the original vector. Now with this encoding over there, let's say your M is 8, and then you have 8 bits, then it's 8 by 8, it's only 64 bits. So you kind of reduced your size by a factor of 64, which means if you have your billion scale data set, you need 8 gigabytes of RAM to store these quantized compressed vectors. How do you estimate the distance now? So here comes the query. Those are the database vectors, but let's forget about them. Let's say they're compressed. So all you're going to see is this list. What you can do now is you take this part, again, the first 2 dimensions, and you know, well, for this vector, the 42th centroid, like centroid 42 was the closest one. You look at this centroid's X and Y coordinate, and you just compute the distance to that. This is how you do the distance computation for the first part, and then you can just sum them up if you are an L2 squared distance. So you can efficiently approximate it. You do it asymmetrically. So you could wonder, shouldn't you product quantize this code first and then do distance computation? Doing it asymmetrically and just keeping the vector is better. You can even pre-compute distance tables. So you know that you're only going to see 256 different values here in this part. So when you see the query, you can, with the query, just pre-compute these 256 distance values and just look them up in a table. And there's this work on SIMD-based distance computations where all of them are in a single AVX register, then, like these tables. It's super fast to look these distances up. All right, if you want to learn more about product quantization, I can say this because I'm not Yusuke. There's a really good implementation that's made by Yusuke. This is all of it. This is like product quantization in Python, in pure Python. It's a tens of lines in Python, and it's called NanoPQ, and it's really easy to install. I give it to all of my students when I need to explain product quantization, right? Because they look at the code and it makes sense. Whereas before, maybe the pre-computation of all of these things didn't make sense. Here it makes really sense. So what did they do in the experiments over there? Well, they use product quantization. And the 4 means 4-bit centroid, so 16 different centroids. 128 by 4 means they split it up, the original vector, in 128 blocks. And then each block had 16 different centroids. FSR is fast scan, which is the AVX-based table lookup. And R means residuals. You use the IVF structure to come up with the product quantization in each of the inverted files. The one on top is like a rotation that improves what product quantization can do. All of these things are against things that you have to set yourself. Yeah, and at least, but the good thing is that they at least tell us what they did. And once you understand what's going on, actually these numbers make a lot of sense, and you can think about, wouldn't it be better to use 64 instead? Right? You lose some accuracy, but you could gain some speed, and you can run an experiment to see if there's a better trade-off. All right. So now what we can do is we have this product quantization at our hand. Whenever I I'm somewhere in this pipeline, I could have said, I can just remove, like I can forget the vectors. I can just use compressed vectors. I can do this on the index part, or I can do this down here when I have to scan through the index. Right, and the easiest way would be to do everything on the product quantized version, compressed version, and then at the end, maybe it might be a good idea to re-rank when you get, because you did this compression that is lossy. So you might not get the true distances, but if you just return maybe a little bit more nearest neighbors and then actually compare distances, then you can still get good recall. Okay. So now there are two choices. What you could do is the first choice, you just build your index on quantized vectors. So you learn your PQ code, you represent each vector by its PQ code. You aim for a code size that is like 32 bytes to 64 bytes, because then you can still put a billion scale data set into your RAM. There has been not much work in this regime on graphs, because graphs, you can compress the vector, but you still have like a billion nodes that you have to store and you pay for it, right? You have to have a billion nodes, you have their outgoing edges, they are actually not compressed, right? You still have to build for that part, you have to pay for this part. So usually you don't use a graph. What you usually do is you use this IVF-based index. So you have like 1 million centroids, index on the centroids, and then your billion vectors in compressed form. If you look at this, you're going to be lossy, right? So the recall quality that you achieve is here 50%, it's here 60%. Those are two different ways to do product quantization if you have the inner product. The orange colored one is the scan library from Google, and the blue one is FICE. If you do re-ranking, you still get very good results, right? But it means that somewhere you actually store the original vectors. You have to open up this box, maybe it's on disk, and you have to compute the actual distances. Then you can get up almost perfect recall as well, if you do that. But I think the interesting thing is even with smaller values, this works. All right. How do you do an out of memory index? Now I want really good performing nearest neighbor search, but I don't have space to store the data set. It has to be on the disk, and I don't have space to store the index. So what this KNN does is the following. It's really clever. So you have your huge data set. And first, you have to ask the question, like, how can I build a graph if the data set doesn't fit into RAM? What they do is they say, well, let this be 412 gigabytes. Let's first run some kind of clustering based on that. So they split it up into different parts where each point is again associated with its closest vector. A really nice trick they do is, now you have your point, let's say x2. Where does it go? It goes to the two closest centroids. It doesn't only go to the single closest centroid, but it goes to the two closest centroids. This is clever because then the single point sees a bit more from the data set. If you don't do it, you get really disconnected graphs, because then there's a certain data set was trained here, and another data set was trained on a completely different graph. It's difficult to merge them. If you do this little trick, you get really well-performing graphs. And you set it in such a way that individually you can build these graphs in memory. At the end of the day, you get all of these graphs, you merge them together. Now I come back to your question. How does the data structure look like? The data structure is in RAM, you have your PQ codes. You just have the compressed vectors. On disk, you have the original data set and you have the graph, and you do it in the following way, that you have a target degree, for example, is R, 128, and you store the original vector, which has a certain dimensionality, and next to it in memory, you store all of these R different neighbors. It might not be that a that a node has r different neighbors, then you just pad with some dummy values, because it's really important to be able to say, so what is the 10,000th neighbor? Where is it on disk? And it's with this padded version, you can just look there. And what they do is, so you have this represents in a single node, it's the original vector and it's the r neighbors. And they set it so that you can read it with one read from the SSD. Yeah, so it doesn't matter. So you do it exactly on that size that your SSD supports. This is what you have this is what you have on your SSD. In RAM, you have the compressed version. Now you have to carry out the search. So how did you call it? You check a node when you do the single. I think there was this part where you are the node and you look at all of its neighbors. What do? Is so you inspect this node, you read all of the adjacent nodes from your SSD. They're right over there in this block. Then you can, as the good part, also fetch the original vector because it stands right next to it. Then you have to compute distances because you have to put them in this candidate list again. What you do is you do this only with the PQ code. So this is lossy, what you put on your candidates. How well is this going to perform? On a single thread, this is still more than 1,000 queries per second. It's insanely fast. And they do it, and this is usually what they do now in Microsoft, right? That they actually use a RAM SSD setup because it's so much cheaper than having huge machines with a lot of RAM. It's much cheaper to have smaller RAM, but an SSD next to it. And this is what you can do when you're out of memory. Yeah, it's a very fast way to store. And it's better than IVF approaches because of the memory layout that they use here. And because graph-based approaches, they don't need to read that many neighbors. That was the whole idea why they good. Okay, I'm out of time. Very recent developments. Let me just say there is a new graph-based approach. That was the one that said that the other graph-based approach doesn't work. It's at VLDB, it's in Vancouver in 2 months. You can check it out over there. And it's interesting, I just pointed out here in the material. We talked about, oh, it's so difficult to choose parameters, and everybody is in this situation. There was a recent paper at ICLR from people at Google. They took their scan and they asked, how do we find good parameters? And they made this optimization problem out of it. And then the solution to the optimization problem says, first do that many clusters, then do that many clusters, then do that many clusters in a hierarchical way. And what they show is that they both are much better than our baselines from our previous competition. But they also show that they were not able to do this like in a systematic manner, right? So their optimization gave better values than the huge grid search that they did before. It's a really nice read. And then, just to finish it, there are other settings, and those are really researchy questions. One of them is filtered search, where you have vectors and you have associated metadata, like from YFCC. And the query is now, give me the most similar image, but give me one where I used a Sony camera in 2017, and it's actually in Vancouver. If you have these filters, everything becomes much more difficult. With these clip embeddings or what they used here in Yandex, often you get a different distance structure of the image and the text encoding. And currently, like nearest neighbor search algorithms really have a problem with that. So this was trained, the index is just image embeddings. And then you presented an image and it performs, I mean, it's still lossy, but it performs pretty good. Then you present it with text and it's much worse. Somehow there is a different distance distribution with the text queries, and it's not well understood. So this is also recent research, and there are streaming settings. Like at Microsoft, for example, they have an index of 1 trillion pages, but their problem is they also get 1 billion updates per day, where they have to change the index. How do you do this? Usually they did daily rebuilds of the index, and it's very expensive. So how can you do this clever update? Why am I saying all of this? There's going to be a new challenge at NeurIPS. We follow up on our 2021 challenge. This is practical vector search. And this time it's 10 million vectors. And it's those 3 tests plus another one. And we tried our best to provide good baselines for the filtered setting and for the graph-based setting. But it's really, I mean, there are no other baselines, I think, than what we did here. And the idea is, please improve on these baselines, right? We're going to announce this very soon. And we're going to give cloud credits for people to try it out. And you can find everything on this website. And hopefully by the end of the week. Right, time frame is that we have to close this competition by November 23. All right, with that said, thank you so much. That was all. Any more questions?
When you're thinking about the amount of information in a million, million document database versus a billion, can you help me understand kind of how much information that would be in a understandable terms?
So I think like the index at Bing, like all of their search engine is a few trillion. So that's the internet for them. It's a few trillion. I think a billion, there's this Lion data set that like, wasn't that where like OpenAI does their training, I think, on Lion, and this is like in the billions.
Okay.
This is for them all of the internet.
Got it.
Yes.
Thank you.
All right. Yeah.
So it seems like doing K-means for in the billions, it sounds like a pretty expensive operation.
Yes.
How much does it benefit from just randomly sending 1 million plus one? You want to do this IVF thing and have it just huge. Does it really matter?
There is an index called extended cluster pruning, which says we do k-means, but we actually do the first round. And so it's extended cluster pruning. It doesn't like it. You have a huge improvement by actually like the extended cluster pruning basically does load balancing, but there's not so much information because this data is actually structured. The idea is to find a structure, and k-means often gives you kind of a good structure. Just doing it at random is not going to be that good. All right, we have 3 more minutes, or what do you say?
Let's wait 8 minutes later. So the next session starts from sorry, this one 40.
Okay, so 7 minutes, and then Han is going to start the third part, and that is going to be much more practical. Yeah, with actually code examples and stuff.
The question with regard to I didn't want to ask you because I don't know if it's really related. There are many people using now sparse embeddings.
Hey, yes.
And wondering if there is any comparison between those approach and more sparse based.
So a fourth chapter that I didn't talk about is ANN sparse data. And it's exactly because there are no good baselines. For doing this on this sparse data.
And that was the challenge.
It's part of the challenge. Test that I didn't talk about.
And so there will be, you will be providing a data set on the
There's a data set. Hey Hans, can you hear me?
Okay.
No, in the smart code.
Hey, yes, yes, I can hear you.
Oh, yeah. So yes, can you share the screen? Pinecone. Like they do the vector. Yeah, they're interesting.
Okay.
I want
Let me try.
Interested in that because one of the dance approaches
Let me
is
look at this.
find a way to combine them still with like lexical matching, right?
Yes.
Okay.
Can you see my screen?
Yeah.
It's set to invest in a full different.
Can you say again? Say something.
A bit complex. But
Can you see my screen? Is this like am I audible?
Well, okay. First of all, I can see your screen. I'm checking the sound. So it's really
Okay.
okay,
1, 2, 3, 1, 2, 3, test.
it's open
can you
already,
say
the
something
challenge.
again?
1, 2, 3, 1, 2, 3, test.
Okay.
1, 2, 3, test.
All right. Yeah, but I think this guy should work. I mean, I'm switching speaker. Can you say something again?
1, 2, 3, 1, 2, 3, test. 1, 2, 3, 1, 2, 3, test.
Oh, wait. Can you say something?
1, 2, 3, 1, 2, 3, test, test. 1, 2, 3, 1, 2, 3, test, test. 1, 2, 3, 1, 2, 3, test, test.
Wait. Why? I mean,
Do you think this is gonna
this
be?
should work.
This should work.
This should work. Yeah, previous. Yeah. Yeah, it's working. Oh,
When you
wait,
use- When you use my output, is
Yeah.
this the?
okay, Han, can you wait a little bit?
Okay.
So we can.
If you,
But if we put this one, then he can.
you can probably not. When you can use the microphone part here and the.
Yeah, I'm trying that.
Okay.
Why? Oops. Why? What about this one here? Oh, yeah, let me. Oh no, that's not. Why this guy is working on? Here, right? This is just HDMI. So this one is HDMI. Oh no.
This seems to be directly connected to that one.
True. Right. So it's impossible.
Did you say that people before
Yeah,
you?
before. I'm not sure.
They want Zoom?
I don't. I thought that this is working, but I have no confidence now. It seems this one is just directly connected to this one. Then. Yeah, that makes sense. What?
How do we access
Yeah.
that one?
Or we can just like put the mic on over there.
This is probably also gonna work. But I don't know if this is, we still need the HDMI. Okay, the HDMI is also kind of there. Did anyone see people using Zoom and?
No, today I was in this room, so.
Yeah.
Not gonna work.
Okay.
All right. Okay. So use that one or this one. That's the which is better. Let me check. Yeah. You know. By the way.
Could you direct his microphone into his computer speaker?
Yeah.
You mean just point it?
Put his microphone into the
Yeah,
speaker.
this is what it is in the other session. They put
What?
The microphone in the speaker.
I mean, we could also try. Oh,
I understand.
you mean? We put,
No, they said in the previous, right? This one. Yeah. Yeah. Try.
What?
Try that.
High tech, you know, to that works.
okay, just
You got to control your volume.
yes.
Let's try. Han, are you here?
Yes, yes, I'm still here. Yeah.
Okay. Now, okay. Now it works. Thank you, Han.
Everything okay?
Little bit.
Yeah.
Okay. Yeah. Can you?
Sure.
Okay. So can you share the slide?
Yes.
This is really.
Yeah, I think so, but I didn't get it to. Maybe like so.
It's working. Han, can you say something again?
1, 2, 3, test, test. 1, 2, 3, test, test.
Okay.
Try again. Test again.
1, 2, 3, test.
Oh,
Test, test. 1, 2, 3, test, test. 1, 2, 3, test, test.
Okay. So it's okay.
Stay away.
Okay. Finally, okay. So finally, our setting is done. So let's move to the third speaker, Han. He will present a very nice work. Okay, Han, please start.
All right. Thank you, Yusuke and Martin, for setting up the all the equipment. So unfortunately, I couldn't join CVPR this time. in person, and I know sometimes it's how awkward it can be when you do a remote presentation, and yeah, because of all the network lag. So I hope in the next 30 minutes or so we can do like you can enjoy this tutorial and learn some practical things about representing, transisting, and especially searching multimodal data. So my name is Han. I'm the founder and CEO of Gina AI. I'm usually based in Berlin. So I come from industry, right? So I got my PhD back in 2014 at TU Munich, and later I worked at Zalando to build a recommendation and search system. And then after I joined Tencent AI Lab to build the search system behind WeChat. Since this is also the the Communication conference, so maybe it's worth to mention that I'm also the creator of Fetch Japanese dataset, which probably many of you have used in your research paper, or let's say in the machine learning 101 let's say lecture courses. Right. So for Gina AI, so the company founded in 2020, we mainly focus on multimodal AI. In particular, we do a lot of search and generative things. We have right now 60 people. Our headquarters is in Berlin, and we also have offices in Beijing and Shenzhen. We did a lot of contribution to the open source community. In particular, we have this Gina and Docker Array, which is let's say the kind of the focus that we are going to talk about in this tutorial, right? So our company mainly focus on these 4 technologies: prompt tuning, which is about optimizing the prompts for large language model and also text to image models, and prompt serving, which basically you can think about LangChain as a very typical framework for orchestrate prompt, which is kind of prompt serving framework. And also model tuning, which is basically fine tuning, as we all know, and model serving, which is the traditional MLOps stuff, right? So this is kind of the tech spectrum of the company. And over the last 3 years, we have developed many open source, closed source products and projects under this tech spectrum, right? Okay, so today's agenda, I want to, let's say, kick in to this topic in a more practical way. So first, I want to give a very short introduction about this multimodal AI. And then we come to the kind of practical usage and introduction about the Docker Array and how the Docker Array can help you to solve the representation, transisting, storing, and retrieving problem. And finally, if we have time, we can see end-to-end examples that use Docker Array to index multimodal data and then integrate it with LangChain. Right? So this tutorial requires, let's say, almost no, let's say, theoretical knowledge, but it does require you some, like say, practical understanding about Python, especially data class, and so on. Right? I will try to make it very, just very basic. Let's say, hopefully everyone can enjoy this tutorial. So let me give some short introduction about this multimodal things, right? So this is a graph illustration that I did last year, right? So that says that in 2022, it is kind of like a turning point for the industry. That before that, most of the machine learning algorithm the applications are mostly unimodal, right? So that means they focus on single modality. The algorithm there can be only used in text or in images, but not both, right? But after 2022, so we start to see, let's say, from DALI, Stable Diffusion, Bleep, Clip, Bleep2, all this kind of models, large models, focus more on like bringing different modalities into the same space, right? I mean, from the academic perspective, let's say the turning point probably earlier, right? But I'm coming from the industry, so I kind of observe this very, very obvious trend start from 2022, right? So here, modality really means a data type, right? So the unimodal AI basically referring to applying AI for one specific type of data, right? So you can imagine most of the early machine learning algorithm falls into this category, right? Even today, if you learn, let's say, machine learning from scratch, right? So most of the machine learning literatures or books basically teach you about how to do machine learning in a unimodal way, right? So to kind of like elaborate this idea, right? So let's say, I want to bring one of my old paper back in 2010 about latent Dirichlet allocation, right? So this term is probably not very popular nowadays, but back in 2010, it was like the old timers transformer, right? So a lot of papers in the conference was talking about this LDA, right? So the idea is basically using some Bayesian methods to model the article document into a multinomial with a multinomial distribution, right? And you do some variational inference, keep sampling to estimate the parameters, and then you kind of have the joint probability of the, let's say, the full Bayesian model of the article, right? Where the article is can be modeled as a distribution, as a multinomial distribution over different topics, and each topic can be modeled again as a multinomial distribution over different words, right? So things like LDA was back in the days very popular, and in many, let's say, tasks in NLP, we have developed a lot of ad hoc methods for solving this problem, right? So that's kind of the very popular task that we found we observed in the NLP conferences, right? So that is a textual modality, right? In computer vision, I also want to bring another paper from me, old paper from myself, the special needs data set, which later becomes the kind of the benchmark data set, standard benchmark data set for machine learning. Although it is very popular, but FashionMNIST is designed for, let's say, for unimodal tasks, right? Whether it is, generation, like I remember back in this, people use GAN to kind of reproduce those data sets and do some classification, of course, regression, all these kind of things. And but if you look at all these tasks in the computer vision, right? So many of them are also like unimodal, right? And here is also like a speech audio. We also have this very popular task, which basically focus on the this speech audio modality itself, right? So if you think about the unimodal, right? So you can think about we are building, let's say we have this cube where each facet is a modality, right? So we have textual modality, visual modality, and so on, right? And but you can imagine those facets are orthogonal to each other, right? So that means the knowledge that you learn from one modality cannot be migrated into another modalities, right? But how can we bring these connections between kind of different modalities? Can we learn something from the text modality and use the same method in the visual modality, or vice versa, right? So if you, let's say, if you travel back to 2010 and join one of the NLP conferences, right? So you probably have no shared topic with them, as a researcher from computer vision community, right? But nowadays, I think if you join, let's say, EMNLP calling, you probably will make some good friends, and the conversation must be very inspiring, as you can imagine. So things have changed, right? But there is a very interesting detour that back in 2010 that there's a NIPS workshop paper that I published which kind of building a very, very big Bayesian model for building the connection between image and sound using text as proxy, right? So in the end, it's kind of like a cross correlation, a latent d-Haslet allocation, which is very, very complicated. Even though the mathematical, from the mathematical point of view, is very beautiful, but in the end, it doesn't work, right? Because this model is just too small to capture all these correlations between different modalities, right? So that said, if you think about this transition from unimodal to multimodal, right, and then you can think about we kind of erase the boundary between different modalities, right? So this cube, we kind of mold this cube into this kind of sphere, right, where the boundary are kind of smoothed out, right? So that also means the tasks can be shared and the knowledge can be transferred between different modalities. And knowledge that we learn from the ARP can be applied to computer vision and vice versa. And of course, all know that how the representation learning and transfer learning plays a very important role in this transition or in this paradigm shift. So, and I believe that from the from now on, and especially in the industry, we will see more and more AI applications that move beyond its own modality, right, and go for like exploring the cross relationship between different modalities. So last year, Yann LeCun said something like, our artificial intelligence systems trained on words and sentences alone will never approximate human understanding, right? So he was saying that under the context of criticizing ChatGPT, of course, right? But it does deliver a message that the future is multimodal, right? The future of machine learning or the future of AI is multimodal, right? So we all agree that the multimodal AI is the future, but it seems that let's say from the machine learning ecosystem perspective view, it is not ready for that yet, right? Well, the academic is ready, but let's say the industry or the tech stack is not ready for that. And that's why we introduced this Docker package. This Docker is an open source package where you can check out this GitHub /Docker. Even though that we start this project is right now under the umbrella of Linux Foundation, which is a neutral open source foundation, vendor free, so that we aim to build Docker with community together and make it really like a vendor neutral, multimodal, let's say, data structure, right? Okay, so let's move on, right? So if we think about this multimodal data, the first thing or the first challenge is, of course, how to represent this multimodal data in practice, right? Let's say using Python, right? Make it even more practical, right? And of course, there is also other problems like translating, storing, and searching, which is neural search, as Yusuke and Martin just talked about, right? So let's first look at the first pain point, right? Representing multimodal data, right? The problem here is we don't have very common interface to represent different data from different modalities, right? So if we look at all the existing popular package, right, the audio, video, image, text, 3D mesh, and each one of them has its own format, right? And it's very hard to kind of glue these two formats together in one data structure, right? And of course, you have different packages, libraries to compute, and then you have different ways to store them into the backend or on the disk, right? But besides that, right? So if we look at just very simple multimodal data, right? So like this newspaper or magazine, right? So you can see that this consists of text and also images, right? if you just like say do this in a very like a naive way, you get of this different sub-documents out of this full documents, right? So, and each sub-documents may come from different modalities, right? And also you can see there's some nested structure, right? For example, this one has it is its own document, right? But inside that there is also an image, right? And so there is also a nested structure for multimodal data. So I will here just give a brief overview how the Docker array solves this problem, but later we will dig in to kind of like a full understanding how does it work, right? So in Docker array we solve this problem by using some like syntax as Python data class, which is let's say introduced since 3.7, right? I think back in 2018 or something, right? So this data class was another way. It's another way to represent kind of like an object in Python, right? And we can use it in Docker array. We improve that. We improve the data class and also the typing system along with this data class, and then so that we can use it for representing multimodal data, right? So for example, let's look at this card, right? So this usually is a news card. I think this particular card comes from Washington Post. And there is a banner image, right? It's of course an image, and there is a kind of tagline, there is a title, and there is author, right? So here we can represent this card as this banner, right? Which is an image class, image type imported from Docker array, right? And then of course the headline is the text, and there is some metadata such as author, column, the name of the column, which is a JSON, right? So this image text and JSON is not, let's say, the native Python class or native Python typing, but it's actually a typing from the Docker array. And this is very important. But we will talk about this typing system later. But overall, you can see that this is how we map or how we represent this multimodal data, this very simple multimodal data using a very simple data class object. Okay, so the other thing that we want to, let's say, another pain point that we are facing when handling multimodal data is if you think about, okay, so this data object consists of image, text, probably videos, audios, and so on, right? And we want to process, right? So for example, let's say we want to embed them using, first using clip model, and then using some video encoder, keyframe extraction, and then do the frame by frame encoding or embedding, and then later analyze the kind of the soundtrack, extract the soundtrack, and then do some embedding of the sounds, right? So it seems that in practice, if we want to implement this system, we have to kind of transfer this object over the network, over different machine learning algorithm, where each machine learning algorithm is, is hosted in a microservice. Right? So you want to transfer this multimodal data object over the network so that each microservice does its own job, right? Of processing, embedding, of pre-processing or post-processing this data object, right? So if we think about this pain point, right? So how can we design a multimodal data that can be easily transferred over network, right? So we can think about the kind of the nature of the data, right? So there is a data at rest, which you can think about Hugging Face data set, which is a very typical data at rest. You just download, you pull the data, and then you do the batch processing on your hard drive, and that's it, right? So it's not a data type or data structure that designed for transferring over different microservices. Right? There is also like a data in use, which is like an in-memory data structure and so on. But here, the Docker array focus more on actually optimized more for data in transit. Right? To do that, we actually designed the Docker array to be ready to wear at any time, meaning that we provide all this very fast serialization to JSON, binary bytes, base 64, protobuf, which is like the favorite data structure when you work with microservice or Kubernetes stuff. Right? And of course, Python is pandas data frame for data scientists. And we also have support, let's say, a push-pull to S3 bucket and so on. Right? So here is some benchmark over the 1 million documents using different serialization, binary serialization algorithm. So you can see we have this protobuf stuff, and you also have this unsafe, but let's say very easy to use Pico stuff and so on with different compression algorithm. Right? There is also a benchmark of this deserialized time. Of course, the smaller the better. So the last pain point, okay, so I want to mention here is storing the multimodal data, right? So as I mentioned before, right? So this Docker array is optimized for storing multimodal data inside, let's say, with the support of the state-of-the-art vector databases, right? But the problem here is especially since this year, there are just too many vector databases popping up, right? And they all have different APIs, and there is no universal client, right? In this sense, you can imagine Docker array to be the universal client that kind of the entry point to access all the vector databases, regardless what the actual API of those vector databases are. So to see that, we can basically, this is how you append a document, how you insert a document using Malware's backend, right? So you just initiate this document array, right? And then you define the storage backend to be Malware's, and then you define some configuration. Here you need to do some connections because database such as Malware's, Pinecone, Vivian, Quadrant, they follow this client server architecture, right? So there is always a connection that you kind of connect to the server, either locally or remotely, right? But to kind of write documents into this Malware's backend, it's very simple. You just do this waste scope as you in Python, how do you write a file, right? You just open the file, and then you just append this document. Right? Here, I just construct an empty document, which makes no sense because it was thrown an exception because it was found, oh, there's no way to kind of encode, or let's say, it doesn't have embedding, associated with this document, right? But it just give you an idea, right? How does it work? But not only Malware's, right? Here you can just switch the storage to Quadrant, Vivian, Elasticsearch, Redis, OpenSearch, ANLite, and even SQLite. Even though the SQLite is not a vector database, but it is fun to put it here, just to show you how does it work universally against all the storage backend, right? By the way, if you use SQLite as the storage backend, the underlying nearest neighbor search will fall back to exhaustive search, right? Yeah. Okay, so yeah, here's a demonstration of how do you, want to work with this vector search. How do you want to do the vector search on this the DA document array object you just built, right? Here, you just put the embedding here and write the limit to 6, which gives you the top 6 like nearest neighbors, and here you get the result. and that's it. Right? So you can easily switch the backend here, define here, and you know, the user experience will be the same. Right? But of course, like you know, the kind of the support on different backend requires not only the maintainer of the Docker array, but also the maintainer of each kind of the backend. Vector database backend, right? So for some vector databases, not all the features are supported. For example, some vector database has this filter things, which is usually are supported by Docker array as well. But you know, this is a continuous effort to keep updated with the state-of-the-art vector databases. Right? So a quick recap of what is, you know, Docker array so far, right? So by the way, we will come to that later about the, you know, the hands-on Docker array. But a quick recap so far is that if you think about this Docker array, it is like a JSON, right? Designed for multimodal data, but you can use it for intensive computation, right? I didn't showcase it here, but maybe later in some slides, I will talk about how to use Docker array object in PyTorch, right? On the other hand, it's also like a NumPy ND array, and this is actually where the name of Docker array come from. So we're actually very ambitious. We want to build something for multimodal documents that as popular as ND array in NumPy, right? So that's why we call it Docker array, right? But designed for unstructured data, or let's say multimodal data. Right? It is also like a pandas data frame, but in this case, you can also consider that embedding is a kind of default field or first-class field for the multimodal data object in Docker array. Right? It is like protobuf, but designed for data scientists and deep learning engineers. Right? So that's kind of how you describe Docker array. Here is also a side-by-side comparison of how the Docker array handle you know, different features and compared to its counterparts like ND array, JSON data frames, and the protobuf. Right? All right, so let's move on to some hands-on on the Docker array and see how we solve the representation problem and the transisting, storing, retrieval, all these problems with some real code. Right? So before we start, right? So I want to point out there are two versions which you know, kind of like give you slightly different user experience of Docker array, right? So one is this the latest version, which is after we donated to Linux Foundation, right? So this is a 0.33, right? And here the this kind of data class user experience is more emphasized, right? And there is an old version, which is 21, right? The 21 has more features and more support on the vector databases, and has a general, like a better compatibility, you know, let's say, you know, when working with PyTorch, right? But here we want to focus on the latest version, this 0.33, right? Okay, so first let's look at how can we represent multimodal data in Docker array, right? So in the let's say in the core of the Docker array, there is a very essential concept. It's called base stock, right? So basically everything, every object, every multimodal data object you constructed is actually come from this base stock class, right? So let's say if we want to represent a banner, website banner image, right, which has a image, URL, a title, and description, then you can define your, let's say, your data class like this. Right? So you don't have to write the, you know, explicit data class decorators here because the base stock already has this implement inside, right? So you just inherit it or subclass from the base stock, and then label the image URL as, or the image as this type, and the title and description as native Python type, native Python string. And how can you construct a document out of this the data class that you just construct? You just define, right? You just give the URL here, title, description, and then that's it, right? Here, this image URL typing also comes with some helper function, right? So for example, you can just do image URL dot load. It will just download the image from the remote or from local, and then load it into memory. So let's see another example, right? So let's say if we want to represent nested data structure, right? Like this, right? So by the way, this is one of my friends, which is like a YouTuber who focus on the fonts and designs, right? I highly recommend you to watch that if you have time. But let's say, for example, let's look at this YouTube, let's say a video, right? So it has a title, description, thumbnail, right? The title, description, and text, and thumbnail is image, and video, of course, itself is a video, right? So let's see how Docker Array can help you to represent all this data into one single object. So first, we need to define the kind of the data class for the thumbnail, right? So we have this image doc, which consists of image URL and also the bytes that are placeholders that we later can use to load the image data into memory, right? This is image bytes, right? And then we have video. The same here. We do the video URL and video bytes, and then we build this YouTube video doc, which consists of title, description, a Python native string, and thumbnail is the data class that we defined previously, this image doc, and the video is the data class that we defined previously, right? So you can see there is some nested structure here that basically help you to represent very complicated data structure, multimodal data. Yes, yeah. So the representation, So here you also have the ability to kind of transfer this object in very easy way over the network that we will see later. So overall, the structure looks like the following, right? So you have this YouTube video doc, right, which has title, description, thumbnail, video. And thumbnail is image docs that you define here. Then video is a video docs that you define here. Okay. So a quick recap of what we have learned so far about representing multimodal data, right, using Docker Array. So it gives you a data class look and feel, right? So if you're familiar with Python data class, right? So then this kind of design pattern should be very familiar to you. You can use this data class to define the structure, right? And it also, let's say, leverage a feature that becomes, let's say, mainstream since Python 3.8, which is a typing system, right? Here you can define, here we extend the Python native typing to multimodal data, right? So in particular, you can define text, image, audio, video, mesh 3D, and a point cloud 3D, right? So those are, even though they are different 3D data, so they have different data structure. And so you can also define tensors, like image tensor, audio tensor, video tensor, and also embedding tensors, right? But embedding, we don't call it tensor because it's usually just one dimensional. And of course, for each types, you can also kind of wrap with optional this modifier to declare that this field is can be none, right? So this is basically fully compatible with Python native typing system, right? Okay, but so far we have just look at how to use doc array to represent a single document. But we all know that in machine learning we don't work with single document. We often work with a batch of documents, right? A lot of documents in one batch. So here we have two representation, two containers that help you to define like many documents, right? Many documents object, multimodal docs. Right? So one is doc list, which basically follows the Python Python list behavior. The other is called doc vec. The vec here represents vectorized, right? Basically, it is column-based representation of the base docs, right? So let's see some example. So let's say we have defined this banner doc, which consists of image, title, description, right? And then we can define we can instantiate two banner objects from this two hello world and bye bye world, right? And if we define the doc list, and then notice the square bracket, which enforce the data type that inside the doc list to be banner doc, no other things, right? So basically, by writing something like this, you define a homogeneous doc list, which can only contains data type such as banner doc, right? So you can put banner 1, banner 2 inside the list, and then convert it into a doc list. And then if you print it out, it will just give you the summary, right? So basically show you that how the schema of the document looks like and how many elements inside the doc list. Right. Of course, you can do element index access and also iterate over this as iterate over doc list as a Python list. Right. The other thing that very interesting is that you can directly visit the attribute that you defined on the member level. But you can visit it on the array level. Right, on the list level. So here, for example, the banner that we defined has this image attribute, right? But let's say you want to access all the images from this doc list, you can just do docs.image, and then it will return to this list. Okay. Yes. But as you can imagine, using this way to access all the images is probably not very efficient, because underneath is implemented as doing a for loop, right? Excuse me. Doing a for loop and iterate over doc by doc, right, inside the doc list. So it's not very efficient. That brings to the other data structure, which is doc vec, right? But before that, so let's iterate this again, right? So in doc list, there are two ways to define the doc list. You can either put your multimodal doc inside the doc list without typing. So here it's basically you want to let's say store heterogeneous data, right? And the other way is to define the typing here, which basically requires all the multimodal doc inside this doc list to be homogeneous. For example, if you do something like doc list image doc, but you put an audio doc inside that, then it will just throw an error, right? But here it is fine, right? But requiring something like enforcing the homogeneous doc list has many benefits. So for example, it's easier to store them. It's also easier to transfer over network, conduct computing over the doc list, and so on, right? And as I said before, right, so doc vec is a column data structure, right? So which allows you to quickly access the attributes like dot images, dot embeddings, where you don't need to for loop over each document because they are already structured in this way in memory. Right? So let's say, for example, you want to embed images into let's say into some, let's say this is your image height and width and these channels, and you want to kind of, let's say this is your clip encoder, right? So this is your clip encoder. You want to kind of take a batch of all these images and output them into vectors. So if you use doc list, and then you define image doc, like this, and then you put all the image doc into doc list. And then when you do the embed, you have to do this np.stack and then do docs.image, which basically iterate over all the image attributes of the stock list, and then later stack them together, and then feed that to the embed functions, which is very time consuming and not very efficient. Right? But if you use docvec, so you can just do docs.image again, right? You're without np.stack, right? And then it will just grab this column, this image column from the memory, and then directly do the embedding. So it's much more efficient, right? Okay, but of course there comes with catch, right? So it's not for free, right? Because in docvec, you cannot easily, let's say, you cannot efficiently add or remove elements compared to, let's say, doc list. But I guess you all know the idea, right? So column-wise and row-wise data structure is each has its own benefits, right? Okay, so let's move on to the storing and retrieving via vector database. Right here we have, you know, as we I think here, right? So here it's just the image doc data structure that we defined, you know, using this base doc, right? And then we construct a lot of image doc and then put them into the doc list. Here we use a very simple HNSW document index, and then define the schema here to be image doc, define the work directory here, and then just do the index, right? And that's it, right? So that's and then when you do the search, when you want to search for nearest neighbors, you just you know, do this index.found, right? Okay, so what does this code tells us, right? So this code tells us there seems like a document index, this new class, right? Basically, somehow we import from document array.index, right? This place, right? Okay, so this document index actually provides a unified interface to vector database. In some way, you can think about this as this ORM of the vector database. So right now in the 0.33, it supports all these vector databases, but in the old version, it supports even more with Redis, OpenSearch, and so on, right? And also Malus, right? Okay, so here is another example. Basically, show you if you want to use this document index, you first import the vector database document index into your environment, right? And then you define the schema here. You again using the square bracket, right? And yes, the column ties. So basically, the embedding, what it does underneath is basically it will recognize the schema and recognize, okay, so this part is something that I want to index as embedding, right, automatically, and this part is something that I want to index as, just a regular text field, so that later the user can do some full text search on this field, and here the user can do some vector search on this embedding. Right? So you don't have to define the schema by yourself anymore. Right? Yes. So here is how you want to. Oops, here is how you want to just index a lot of documents in one batch. You basically define the doc list here, and then as long as the schema is compatible with your remember, this DB object is a document index object, right? So that we defined at here, right? So as long as the schema that we defined here is compatible to the schema that we defined for the doc list or docvec, So you can directly feed the data into the document index. Yes, so as long as it is compatible, then you can directly work with that. So when it comes to vector search, as we said previously, and I showed previously, so you can simply use this .func function and then search over this embedding field that, previously we defined the embedding field here, right, as the something that we want to index as, as a vector field. Right? So later that you can retrieve it via nearest neighbor search. Of course, you can also search by raw vectors. You can just construct your embeddings or accept embeddings from user query or OpenAI and then do the search. Right? You can search over search a batch of documents and of course search a batch of vectors. So the underlying search is, of course, using the whatever backends that that defined behind this DB object. Right. So here in this case, because DB is using HNSW-lib, right? Then the underlying search is conducted by the HNSW. Right? You can also do the hybrid search, which consists of full text search, filter search, and vector similarity search in one shot, right? So here you need to build a query, which is come from this DB object build query, right? So you can define your query, compositional query in this chained way, right? And then you define a query object and then execute the query against this DB object. So this will give you one shot doing the hybrid search. Of course, you can customize your DB configuration as such, right? So if you are like an advanced player, you want to play with all these parameters, you can also do it very easily, right? Okay, so let's see, what is this? I forgot what I write here. Okay, so here let's look at this YouTube video doc example again, right? So let's define all this. Let's see how can we store that and search that very easily, right? So as we said before, this can be considered as the multimodal doc, right? It consists of image doc, video doc, and the overall highest level doc is called YouTube video doc, right? Which contains of this, right? Consists of this, right? Here we basically define a tensor, but to be honest, this should be called embedding. It's just a naming conventions, right? Here we define the embedding should be like 64 dimensions, 128 dimensions, and it should be compared in the cosine space, right? Using this field stuff. This field is actually a Python native typing, a feature in the Python native typing system, right? And then you define the index docs, right? To be kind of all this, a list of this YouTube docs, and then you just do the index, right? That's it, right? So basically here you can see, define the schema as HNSW document index, and then you just put all the doc list that has this schema object into the doc index. During the search time, since we have so many fields here, right? Then we can search over thumbnail, which is 64 dimension embeddings, right? We can also search for videos, which is 128 embeddings, right? We can also search for descriptions. Right? So basically what you need to do is basically just search for, target, specify the search field using this double underscore or underscore, right? The syntax, right? To define which field you want to focus on, right? And then this will conduct the similarity search on that particular field. Right? Of course, you can also say, oh, I have a better way to concat the textual embedding and video embedding and thumbnail embedding into one big embeddings, right? The easiest way is just to concatenate them together, which is not a very good idea, right? But let's say you have this on the highest level, you have this, this meta embedding, right? For all the information that you have in this video doc, right? Then you can also search for this meta embeddings here, very easily. Okay, so I think I'm like almost out of time, but here there are also like a doc list that you can use. You can use sub index. Okay, so this is actually very interesting, right? Probably worth to mention here is that if you have this nested structure where one of the field is actually another doc list, right? Then the indexing could be a little bit complicated than the kind of the plain nested structure that we talked before, right? Because here is kind of another level of vector database, right? So here you can imagine there's a sub level. You can also construct the embedding index under this this field, right? Along with the parent. With the topics level index, right? But fortunately, you don't have to handle all these things by yourself, right? Again, if we recognize there's something that is another container structure, right? At least a VAC inside your multimodal doc object, we automatically construct the sub-index and tell the vector database so that you can later search for that. Right? So basically here you can just say, okay, so I have a field called docs, right? And I don't want you to search over the parent index, but I want you to focus on the docs of each element, right? And I want you to focus on this sub-index. Right? You can also do this dunder syntax over the sub-index, right? As we said before. Okay, so let's quickly go over the last pain point, which is the transiting data or transferring data over network. Many people when look at all this data structure, like a typing data class, typing system, they actually don't know why bother even to do this, right? As I said before, one pain point is how you transferring the data into over the network. Let's say, for example, right now the most popular Python framework, which is Fast API. And then here, if you define the data structure like this, right, data class like this, you can easily use Fast API and enforce the input and output, the type of the input and output. And then the Fast API will basically recognize, oh, there's an input doc, so the whatever comes from the JSON must follow the schema that defined here, right? It must have this, image doc, which is like another document that you define, and it must have this field, a text field, which is a string, right? And the output docs must follow this ND array, this embedding clip and embedding BERT, right? So must follow this format. Right? So that it does the automatic type checking over the network, right? So that you kind of filter out a lot of nonsense or malicious requests automatically. You don't have to implement all these things again, right? Of course, if you just do something like this, it also automatically converts the incoming JSON into the input doc, which is basically the things that you defined, the schema that you defined here. And then you can directly do doc.image embed, and then get the clip, and then doc.text embed, and get the BERT embeddings, right? And then you return the docs. Right? So that's a very easy way to work with. If you want to build your multimodal data and transferring that over network, this is one very easy way to do that, right? Yes, here you can just show you how to use a Python client to communicate with this Fast API server. But in general, in practice, it may come from everywhere. It may come from JavaScript, from browser, from curl and the bash. As long as it's JSON, it will automatically translate into the schema when it reaches Fast API, right? So another way, if you work with microservice, you probably want to use Gina as a backend, right? Gina is another open source project from our company, right? And so it supports this gRPC and the WebSocket as a communication protocol, right? So here you can also just define this docs as a doc list that follows the schema, and then you can directly work with your magical machine learning algorithm, and then return this as doc list response, right? And that's it, right? So for example, here we just use OpenAI Whisper. I think this a transcription model, right? So to transcribe your audio into text, right? Yeah, here are some deployments that once deployed, you can just send audios with your audio URL, this schema, and then easily communicate with this microservice, right? Of course, you can also chain all this microservice together and do some very cool stuff, but unnecessary on Kubernetes, right? But that's another story, right? Okay, so finally, I think we don't have time, so let's quickly go over this very simple examples. There is actually a very a big example, so where you can visit here. So you basically use build the data schema, input docs, output docs, and then use PyTorch to do the computing. Do all the hardcore stuff, right? And then storing using some vector database and retrieval. Right? But let's move on to this, this long chain, very simple, let's say, example. So, here the idea is we don't want to host any models, right? So we don't want to use self-hosted models. We just use OpenAI's embedding API, right? So let's say we define the movie doc as this, string year, and then we have this embedding, which is this 1,000 something, right? So this is returned by OpenAI, right? Here we just define 2 movies, but you can import the movie from IMDb database, right? And then you construct this doc list as a movie doc, right? And then do this embeddings, embed query, and get all these movies, right? And you construct all the docs. And then you can, here you can choose all a backend index that you want to work with. Here, since we just only have 2 data points, right? We just use in-memory exact search, right? It's a nearest neighbor search, right? So we define, remember, this is document index object. So we define this index, we specify the schema for this index, and then we put the docs into this, right? But of course, you can also use others if it becomes bigger scale, right? And finally, we just do, some of you probably know that we have this retriever objects from the long-chain retrievers, right? We initiate this Docker array retriever, which, long-chain right now supports this Docker array, right? Natively. So we initiated this Docker array retriever, specify the index as the DB objects that we have before, embeddings as we get what we found. I think there's some typos here, so this embeddings should not be written in this way, right? Oh, maybe it does. Okay. Oh, yes. The embeddings is just object from this OpenAI embeddings. Yeah. And then so you specify the search field and content field, and then you build the models, and then do this conversational retrieval chain, and then you get it. This QA, very small QA chain that you can plug and play anywhere else, right? In the end, you can ask questions like, which horror movie do you recommend for Friday night? And then you can ask, use this QA objects QA chain that you just built, and then ask this question, and you get the result. So it's very simple. Okay, so that's basically all the content that we have. I have for this tutorial. There are 2 things that I recommend you to read further. So one is the the kind of the original motivation of building the Docker array. So you can refer to the blog post that I provided here. Basically, show you some interesting story behind why we started this project since 2022, right? In January, when we start to work on this Docker. And the other thing is this benchmark vector search database with 1 million data, right? So Martin will be so mad at me because he was talking about trillions data, but here I just say 1 million data. So here's the idea is if you look at a lot of seasoned developers these apps, right? So whether it's Chat PDF or some other thin wrapper app built on top of OpenAI's API, right? And especially like for example, this Auto GPT, Baby AGI, all this stuff, right? A lot of them they do not need vector database, right? To be honest, right? The scale that they have here is at most thousands, or 10,000, 100,000, at maximum, right? Because they want to store all this agent history, right? Sync chain of thought into vector database, but because at this moment the latency of the GPT and also the cost of GPT is so high that you don't want to store all the chain of thoughts into vector database, into like a trillion level vector databases. So a lot of time, what you need is an in-memory vector database, right? A light version of the vector database, and sometimes even just the exhaustive search or exact nearest neighbor search would do the work, right? So in this benchmark, this is something that we write, let's say, last year, right? That benchmark all this vector database backends that we support, right? Vivian, Quadrant, SQLite, sorry, I always put SQLite here. It's just very fun. Elasticsearch and Redis, right? And here we benchmark from the very engineering perspective, right? Considering all this, read, write, network latency, all the stuff, right? And then here are some results, right? Surprisingly, right? If you just do in-memory exact search, right? The latency is just, let's see, found by vector only takes 0.4 seconds. Well, of course, others like a better vector database can do much better, right? But if you compare this 0.4 seconds on 1 million data, compare this latency versus the GPT-4 latency. Well, this is acceptable, right? Because GPT-4 will probably take 4 seconds or 4 up to 10 seconds, right? 0.4 means nothing at here. Right? Okay. Anyway, so that's it, and I'd like to thanks for your attention for this tutorial for whoever who has come through this long, and I hope you enjoy all the 3-hour section that Yusuke, Martin, and I brings to you. And if you found my talk interesting, you can check our website, follow us on Twitter, or if interested in any other things. In me, just shoot me an email, and that's it.
Well, thank you, Han. So, any questions from all audience? Okay, so got it. Thanks again. Okay. So, Han, thank you. So let's close the Zoom.
Yeah, thank you a lot. Yeah.